had its effect. So this morning we're going to have a series of lectures from my colleagues here in CDD. So we start with Isla Simpson. She's an expert in climate analysis, and she also really impresses me. She bikes up the hill all year, whether it snows or rains or whatever. So anyway, go ahead. I'm not sure you're going to talk about biking.
No, there's no biking in this talk. Yeah, so I was asked to talk about idealized modeling, and I'll be doing that kind of within the CSM framework, kind of telling you about what we have available within CSM in that context. And then also I have a few slides at the end about international MIPS. I feel like these two things are kind of on opposite ends of the scale. Idealized modeling is kind of very simplified versions of the model for understanding, and then international MIPS are, of course, using the latest and greatest comprehensive version of the model in coordinated experiments. So GCMs, or Earth System Models, are very complicated. There are different components, and I think mostly here you've been focusing on the atmospheric component, and they're coupled together with the coupler. This is kind of what CSM looks like. But even if you just take one of these components, the atmosphere component, it's very complicated. So you have the dynamical core, which I guess has been the focus of this week, so solving Newton's laws and the thermodynamic equation on a grid on the sphere. And then you couple that to a whole host of physical parameterizations. And so those are trying to represent these small-scale processes. They're too small scale to be resolved on the grid. So instead, you're kind of representing them statistically in terms of how do they vary given the larger scale environment that they sit in. And then if you're just running atmosphere only, you still have to couple to the land surface in some way, whether that be the land with prescribed sea surface temperatures and sea ice, or some other kind of ocean component. So typically what we do with these big GCMs is we'll run them through a big supercomputer and come up with some representation of what the climate looks like. This is precipitation and sea level pressure, stationary waves in the CSM2 large ensemble. And then we'll perturb it in some way, like rising greenhouse gases following some scenario, and look at how these features change in response to that forcing. And so that's great, but the challenges come in and when you want to try and understand why are these big models doing what they do, and understand the processes involved. And that can be difficult for a number of reasons. One is the CSM or these other bigger models are very complicated. There's many processes, they're all changing all at once. And the system is typically in a kind of quasi-equilibrium state. So you change something, everything else responds to obey these balances. And so that means that all these components are very strongly coupled together. They're responding to a forcing to get a new balance. And so you're often looking at it once the whole system has evolved to this new state. And it's hard to say, well, we changed this thing and that caused this other thing because of these reasons. And then, of course, to get the answer, you have to use a giant supercomputer, which kind of speaks to the complexity of the problem. You can't just kind of think about what's going to happen and understand it. And so how can we then pull apart the responses we get in these big models and understand what they're doing? Well, you can go a long way by just diagnosing model output. You can use simplified versions of the model, and that's what I'm going to talk about today. Or you can perform idealized experiments with the comprehensive version of the model. So the focus for the bulk of this talk is on the simplified configurations that we have available here within CESM. And so we've been growing the capacity to run these idealized models within CSM for a number of years now, and the hierarchy is pretty well filled out. If you're interested, I encourage you to go to the Simpler Models website. I think you can also just Google CSM Simpler Models and come up with the right page. So simpler models are kind of stripped down versions of the model that they only contain certain components, or they have idealized representation of certain components. And there are advantages and disadvantages. On the advantages side, these simplified models, they're very easy to perturb. And so that allows for idealized experiments to look at causal pathways. You can change one thing and you can see how other things respond. They're cheap to run, and so you can run many experiments. And then that means you can do parameter sweeps and kind of look at sensitivities to different states within the model. And then on the disadvantages side, there's just one I can really think of, and it's a big one, though, that they're less realistic. And so if you're using these idealized models, my advice would be to kind of always keep your eye on what the real world is doing or what the comprehensive model is doing, and kind of make sure that what you're interpreting from these idealized models is relevant to the kind of more complicated system. So I'm going to start out with the atmospheric simpler models that we have available. And so this is the atmospheric model hierarchy. So on the lower left here, try and use these things. We have configurations where you're kind of changing the equations of motion that are being solved. And we don't have these. I don't think it makes sense really to put these into a big Earth system modeling framework. They can kind of be standalone things. But then as you go up this diagonal, these are all configurations that have the full dynamical core, which of course you've been focused on this week, but simplifications in the physics. So from the most simple down here up to the most complex up here. And then here off on its own is the single column model, which is kind of the opposite. It doesn't really have dynamics. You're prescribing what the large scale circulation is doing, giving it the fluxes into the single column, and then you're just solving for what that single column is doing in terms of the physics. And then up here, these are configurations that are kind of available. The nudging is definitely available. Cloud locking, Brian Medeiros has done a lot of work with that. It's not fully supported, but it's possible. And those are ways in which you can use the full model and perturb it. And I'm not really going to go into those in any more detail. So here's where we're at in CSM with the availability of these configurations. So all the ones that are colored are available now in a version of the model that you can download. And so I'll just run through these one by one. So the dry dynamical core, I expect you've probably been doing things with this this week. So basically what's done here is you take all of the physical parameterizations and you strip them out and you replace them with a simple Newtonian relaxation of the temperature field towards the specified equilibrium temperature profile. And then instead of all the complicated boundary layer scheme, you have just a simple linear drag on the winds at the lowest levels. And so this configuration is good if you're wanting to look at dry dynamics in a cheap way. So you have a representation of the jet streams and the role of the eddies in the jet stream. And you can easily perturb it. So for example, you can just change the relaxation temperature profile and mimic some feature of global warming, say Arctic amplification, and look at how the jet streams respond. Those are the kind of experiments that people typically do with these configurations. It's good for stratosphere, troposphere coupling as well. But of course, there's no moisture, so anything that you want to do that involves moisture, you can't really do that with this configuration. So if we move on up the hierarchy, though, then we have the dynamical core with idealized moisture. And so this is a configuration that's been pioneered by Christiana's group. So the added complexity here is that you now have a representation of moisture. You've maybe been using this week as well, I'm not sure, but you have a water-covered Earth. Water can be evaporated from the surface. It moves around with the circulation. It can become saturated and precipitate out, and you get heating associated with that. And so you now have some representation of how moisture could be interacting with the circulation. And so this is good if you want to look at kind of dynamical processes cheaply and have some representation of how moisture interacts with the circulation. So for example, here you have a precipitation field that looks like somewhat realistic, where of course in the dry dynamical core you had no precipitation at all. The gray radiation aquaplanet, this is the most recent configuration that we've added to the hierarchy. And so the enhanced complexity here compared to the dry dynamical core with moisture is that this configuration has a radiation scheme, but it's a very simplified one. So you have one incoming shortwave band and then one long wave band, and you specify the long wave absorber. And so it has some representation of radiative processes, but things like moisture are not being seen by the radiation scheme, and there's no clouds. So it's still very simplified and very cheap to run. But you can use it to do some idealized experiments to look at the role of radiation in the climate system. So for example, you can increase that long wave absorber and kind of mimic the effects of rising CO2. So this configuration is in CESM following the work of Darg and Frierson, and it's good for idealized studies where you have interaction between the circulation and moisture, and you have radiation, but in a kind of simplified setting. So moving on up the hierarchy now, these configurations are not really that simple. So we have radiative convective equilibrium world. And so this is using full physics, but the simplification is now in the boundary conditions. So you have a uniform planet, you've got uniform insolation, you've got no rotation, and you really have this balance between convection and radiation. And it's kind of good for looking at processes in the tropics, or so for example, deep convection. So here is an example from a paper by Kevin Reed, where you look at, you can see this is showing outgoing long wave radiation and precipitation. And so it's kind of telling you what convection is doing at different temperatures. And you can see that here it's becoming more aggregated at the warmer temperatures. So that's the kind of studies you can do with this idealized radiative convective equilibrium world. And Brian is here. He's an expert on this configuration, and I'm sure can answer your questions on that. The aquaplanet is, again, not that simple, but with the simplifications here are really in the boundary conditions. And so this is just using full physics. Now it has all the rotation and the varying solar insolation, but it's just a water-covered Earth. So you just don't have the asymmetries associated with the land surface. And so this is good if you want to look at kind of the full physics processes, but you can kind of get your statistics pretty easily because everything is zonally symmetric. And so as an example here, this is from Brian's paper looking at the representation of tropical waves in this configuration. It's also been used quite a lot to look at tropical cyclones and how they depend on kind of large-scale features or rotation and things like that, because you have just a full longitude circle where you get tropical cyclones developing, and you can get the statistics with kind of limited number of years. Okay, over here by itself is the single column model. And so this is, again, the opposite of kind of the other configurations. So there's no dynamics. You're prescribing the large scale circulation, but you're simulating the processes in this single column. So this is good for if you want to look at what's the impact of a new parameterization or changing parameters within the model. You can look at how the physics behaves under this constrained environment of having the same large-scale circulation. And you can either force it with large-scale circulation from observations or from the model. So now I'm going to move on to some new things that we have in the works or recent things. So one is cheaper, comprehensive atmospheric physics options. So I think this is becoming more and more important as we move to more and more expensive models and higher resolution. So within CAM, we'll soon have 4 different physics packages that have happened over the evolution of CAM. And they've gotten more and more expensive if you focus in particular on this one or this one. It's kind of telling you the cost of the model and how that's increased as we've gone from CAM 4 to CAM 6. And so if someone has limited computational resources or you want to run at really high resolution, it becomes really challenging with this comprehensive and very expensive physics. CAM 7 is going to be even more expensive. And so, but there's still a lot that you can do with these older physics packages. They have the representation of many of the important processes that you need. They just don't have the latest and greatest in, say, aerosol microphysics and things like that. So if you don't care about that, there's a lot you can do with these cheaper physics. And these are soon going to die within CAM because of software engineering things. But we have a project to kind of refactor the code and make sure that they still work, and we'll hopefully make kind of somewhat supported configurations of CAM4 and CAM5-like physics available within CESM that can be continued to be used moving forward. And those are good for, so if you wanted to do, say, a coupled idealized configuration and you need to spin up an ocean for a really long time, it would be really hard to do that with CAM7 physics because it's so expensive. But if we can keep these alive, CAM4 in particular is very cheap to run, and so that could be a reasonable option for that kind of experiment. Okay, I'm going to talk briefly about simpler models that we have in the other components. So starting with the land, there's this simple land interface model, or SLIM. So this was developed by Marisa Legou at the University of Washington, or she was there doing her PhD. And so the idea here is this is kind of telling you the processes that we have in the full land model within CESM. And so it's very complicated. There are many processes, and it's really hard to perturb this. So say you wanted to do an idealized experiment where you change the albedo. The albedo is kind of an emergent property of all of these processes within CLM. It's kind of hard to do. So what Marisa has done is develop this simpler model, which is basically going back to kind of the olden day land surface models. So it's much simpler. It has this simple bucket hydrology. You can specify the land surface albedo, the land surface roughness. You specify the depth at which vegetation becomes covered by snow. And then you just have a simple representation of the transfers of heat within the soil. And so what you can do with this simpler model is you can perturb things easily. So if you want to change the albedo, that's just a parameter that you feed into the model. If you want to change water availability, you would just change the depth of this bucket. So if you've seen me give this talk before, I've typically been, I feel like I've been saying this for years now. It is coming soon, but there is a software engineering backlog. Definitely the priority right now is getting CSM3 finished. But it's still a priority, and it does work. If you're really interested in using this, send me an email, and I can put you in touch with people that can help you. It's just not in a kind of fully released version yet, but hopefully it will come soon, probably after CSM3. Okay, ocean simpler models. So there's been one new development on the ocean side, and that's this pencil model. So this has really been led by Young-Oh Kwon and Gokhan here. So this is kind of a depiction of ocean model hierarchies. So you go from a specified sea surface temperatures here to having a slab ocean here. And then on the most complex side, you've got the full 3D ocean model. And so this new pencil model is sitting somewhere in between the slab ocean and the full 3D model. So the slab ocean is basically just kind of a swamp. You have the thermodynamic impact of having a layer of water there, but you don't have any dynamics going on. And you have to specify certain things when you use the slab ocean, like what the depth of the slab ocean is, which is kind of trying to mimic what the depth of the mixed layer in the ocean is. The advance in the pencil model compared to the slab ocean is now you kind of have a full kind of single column ocean model at every grid point. So you have the full mixed layer physics represented. So you have prognostic mixed layer depth. So you don't have to specify that in the pencil model, but you have kind of prescribed large scale circulation. So it's pretty nice configuration, and I just heard from Young-Oh yesterday that they've managed to now complete a several hundred-year-long pre-industrial control, and they're working to make this available. So you can expect that to be coming soon, and the data to also be made available soon. Kind of the last topic on idealized modeling, I just want to mention this new tool chain that's been developed for coupled idealized modeling. So the idea here is that this will guide you through setting up your own configurations where you define the ocean bathymetry, the continental geometry, and the land surface properties. So suppose you wanted to generate this ridge world here where it was a kind of aqua planet and you just have this ridge of land. Or suppose you wanted to look at what is the impact of having a kind of idealized triangular continent and then changing having kind of coupled ocean prescribed SSTs or changing the land surface properties. If you wanted to do this previously, it would have taken a lot of knowledge of CSM and a lot of time to get all of the input files that are needed to set up these kind of weird configurations. And so what's happened in this project is, that particularly due to Alper Altuntas, is there's this new visual case gen GUI has been developed. I think also if you just Google visual case gen, you can find it, or you can go directly to this link. And so this is a really nice tool that can kind of visually guide you through setting up these configurations. So this is just an example of the kind of steps you would go through here. So you can pick and choose the components of the model you want to use, and it will give you guidance as to which ones fit together. You can make your own ocean model grid, and then you can also kind of modify that in terms of kind of the land surface properties. So in this example here, you'll notice that the Indian Ocean has been filled in with land. This is kind of the kind of things you can do very simply now with this tool, and it will guide you from start to finish, to actually creating the case and all of the commands that you'd need to make kind of unusual configurations like that. Okay, so I'll just finish up with a couple of minutes on international MIPs. So MIPs are model intercomparison projects, and so those are kind of coordinated efforts where all the models from around the world run the same kinds of experiments, following the same protocol. And of course, CMIP, the Coupled Model Intercomparison Project, is a big one, and that feeds into the IPCC reports, at least for the last 3. And so these are really a great opportunity to compare models. They're all on an equal footing, having run the same experiments, following the same protocol. And they're useful for updating our projections of what's going to happen with the latest and greatest models and the latest and greatest scenarios to then feed into these assessment reports. So I think you can kind of divide the experiments that go into CMIP broadly into 4 categories. I'm not sure everyone would categorize them this way, but I thought it seemed sensible. So you've got experiments that are trying to characterize the model behavior. So for example, pre-industrial controls and abrupt 4 times CO2 simulations. Those are not really realistic settings, but they're used to characterize the model by, for example, calculating equilibrium climate sensitivity. Then you've got experiments that are used to interpret the historical record. So historical experiments, obviously, and then detection and attribution model intercomparison project that they run single forcing experiments, so you can parse out the role of greenhouse gases and aerosols, for example. Then you've got experiments that are used to predict the future. So in particular, scenario MIP is part of CMIP that is running all these different scenarios into the future. And then there's DCPP, which is initialized predictions into the future. And then you've got many different experiments that are kind of targeted for process understanding or to explore particular climate states. So for example, GeoMIP is running kind of idealized geoengineering experiments with the models to explore how they behave under those kind of conditions. So I'll just kind of go through the plans for CMIP-7. So CMIP-7 is kind of about to get underway. As in other CMIPs, there's the deck, which is kind of the entry card for models to participate. And that's a series of experiments that are really needed to characterize how the model is behaving. So things like the pre-industrial control and the abrupt 4 times CO2. And then something that has evolved a bit now compared to previous CMIPs is that there's kind of more of a continuous process. But in particular, there's now this assessment fast track, which is a subset of all the experiments for CMIP that are the kind of the priority ones that are needed to feed into the next IPCC assessment report. And so the expected timeline to complete those experiments is January of 2027. And then beyond that, all these other experiments that are maybe lower priority for IPCC, but still useful for us in the scientific community to intercompare the models, they can happen more continuously on a more relaxed timeline if they want to, compared to the assessment fast track. So this is a summary, a figure I just took from the CMIP website. You can go and have a look at it there. And these are all the experiments that are going to be part of that assessment fast track, the kind of priority experiments that are needed to be analyzed for the IPCC report. Okay, so to conclude, simple models I think are a very valuable tool for gaining process level understanding of the climate system. Many of them are cheaper to run. Some of them you can even run on your laptop. The single column model is very easy to run on your laptop in a container. I think we also have them pretty well documented at this point. And if you are interested, you can go to the Simpler Models website. If you're running these models and you have issues, you can post queries to the CESM forum. And then I think the international MIPs, those are really a great opportunity to test and intercompare our models, provide up-to-date information using these models that can feed into kind of policy making and adaptation measures through things like the IPCC report, to interpret the historical record as well with our kind of big comprehensive models, but also come up with fundamental understanding. I think there's a lot we can gain by looking across these different models and seeing how they behave differently to understand kind of the processes that are involved in how they respond to things like rising CO2. So if you have any questions or want to follow up on anything, that's my email address, and thanks for your attention. Happy to take any questions.
Questions?
I had two. Is the pencil ocean sufficient to see things like tropical cyclone wakes?
I guess it depends whether they involve lateral motion within the ocean. I mean, I guess you would see definitely the mixed layer responding, but you wouldn't have the horizontal flow responding. So I don't have enough knowledge of whether that's important for those, but.
And then I hadn't heard cloud locking before. What is that?
Yeah, so Brian can probably explain better than me, but it's basically where you can take cloud fields from a different run and kind of specify them so that the radiation scheme is seeing the clouds that you specify. So you basically are locking the clouds and not letting them respond to what you're looking at. So for example, if you just ran with a year of cloud fields from some random year in the model, and you'd have ENSO happening and things, but the clouds would not be coupled, so that you wouldn't have those feedbacks to ENSO. Or same with rising CO2, they wouldn't be responding.
Thank you.
And anything to add, Brian?
No, that's right.
Okay, go ahead, Kenneth.
What are the radio transfer schemes used in the higher order idealized cases like RCE and the Alpha Planet case?
They're using the full standard radiation scheme of CAM, so RRTMG, and soon RRTMGP, I guess.
So for the second part of the talk, you were talking about international MIPS, and like one thing that was relatively new in the last report was a greater role of simpler emulators. Is there a discussion of like combining the first half of this slide with the second amongst modeling groups to have like process-based emulators in these intercomparisons?
Yeah, I think there's definitely stuff going on in that area, and I expect there will be emulators within CMIP, but I haven't been part of that. I don't know more than there are discussions. I don't know if anyone else knows. Yeah, I think it's almost certainly there'll be more stuff with emulators happening in the next one. Yeah.
Yeah, it's more like a comment because you pointed out the dry dynamical core experiments, but in your description you already had forcing actually on the right hand side, which was the thermal relaxation, the Hertz-Rauris forcing basically, and valley friction. So we are even simpler here in DCMIP with no forcing, for example, like adiabatic.
Oh, so I should have had another
We
one.
could have another bullet, I guess, even in that category, or a sub-bullet.
Yeah.
You had a question?
So for the RCE version of the CESM, does the model prescribe RCE all of the globe or just in the tropics?
I think the whole planet,
Whole
right?
planet.
Yeah.
Okay.
Yeah.
question? Go ahead.
Thanks. I don't think I heard anything about the CMIP-7 models. I don't know if you're able to speak to that, but I wanted to know how different are they going to be from the CMIP-6, and are they going to be better at certain stuff? Because, I mean, the CMIP-6 models are doing quite well, but how different are they going to be?
Yeah, so I guess every modeling center is going to have advances or updates. Whether that makes them better, I guess, is an open question. But I think the big thing that will be an upgrade from last time is that there's been a big push for many models to run with emissions instead of concentrations and a fully interactive carbon cycle, so that it could lead to worse representation over the historical, but we have then a whole set of processes that are interacting that weren't there before. And so I expect probably we'll find about half the models maybe will do fully interactive carbon cycle and running with emissions instead of concentrations, and then the other half is probably still concentrations. But that to me is going to be one of the biggest changes in CMIP-7 compared to CMIP-6.
Colin, you had a question?
I was mostly just going to say, if I was a student and I was interested in developing a simple model configuration or helping with the development, what would be my steps to interact with the NCAR developers?
Yes, good question. I mean, I think you probably saw with the land case that it is a challenge to get these to be prioritized in terms of the software engineering, and resources are really needed. So, but we have had a lot of support from NSF, where university PIs have written a proposal and they've included funding for software engineering resources here that can then be used to actually implement the configuration. So I feel like the steps would be, first, get someone at NCAR who has the expertise to be a collaborator, and then think about how to get resources for the software engineering side. There is another thing which I kind of keep meaning to do but haven't really done, is kind of set up a kind of recipes page where it wouldn't be supported within CESM, but where users could kind of go through the steps of what they've done to get a configuration. And so I would definitely be up for examples if someone has a configuration that they want to illustrate how to do it on the Simpler Models website, then we could start that kind of page in a more informal way.
All right, let's thank Isla again. For a while. For those of you who've heard about the ZM scheme, he's also an expert in the circulation associated with deep convection. We've had many talks where we've been referring to the physical parameterizations, but we haven't really dived into what they are. That's what Rich will do. So take it away.
All right, so I know I'm at the DCMIP when I'm speaking on the last day and not the first, because it's physics. Okay, so I'll try within just short of an hour to describe the physics, not only just in the most recent version of the model, CAM67, but I'll touch on a few other aspects of previous versions. Of course, it's very complex. It's been, a lot of effort has gone into this, not just me, but many people in this room and outside this room. So I'll try and keep it somewhat general. Is it just a click to advance? Spacebar. Oh, there we go. Sorry. So just in a general sense, I mean, obviously atmospheric physics, distinct but obviously coupled from the dynamics, and we're talking about many aspects of, in particular, the troposphere here, moist physics, aerosols, surface interactions. But in terms of when you're thinking about how to represent these, and I'm going to focus predominantly on a CMIP kind of class model, so coarse horizontal model. So we see moist and dry processes, small and large processes. So obviously, clouds can form on very small and very large scales, microphysics, very small scales, short and long term. So in terms of stratiform clouds, for example, in the Arctic, they can have a very long lifetime versus very short-lived cumulus. Significant process dependencies. Maybe that's the most difficult thing to represent in the models. We see lots of arrows here, and obviously that indicates that there's interdependency amongst all these processes. And then multiple scale interactions. So it's not just one cloud of a certain scale interacting with another cloud. It tends to be on multiple scales. And goes without saying, with this crowd in the room, all of these versus via transport characteristics and tendencies that are for the momentum, et cetera, from the physics will obviously play into the dynamics. Now, I just want to emphasize that I'm going to talk predominantly about what's happening in the troposphere here. And so, but this is not a singular model or region we focus on. We have a number of models. They may have talked about this already. Apologies if they have, but we have a low-top version which goes to around 40 kilometers, and then a kind of mid-top version, and then a WACAM version. And each of these are designed to represent in increasing fidelity various levels of the atmosphere. There's even one at 500 kilometers, which you need a rocket ship to get to. But the emphasis here is all the tropospheric physics, in principle, for release versions of the model are seen in all these different versions. So how can you group the atmospheric processes in terms of what we're trying to do? The most important one, it's a little tricky, but this is the way I'll do it. So essentially the first thing is atmospheric turbulence. We want to represent the turbulent, particularly the vertical turbulent modes, variability in the atmosphere. This is a very high resolution LES over a urban area, and we can see that there's a significant amount of turbulence there. But of course, we're dealing with something that's 100 kilometers, and so we're trying to represent that. And that brings in aspects of turbulence, mechanical buoyancy, but also clouds and condensation. Radiation, you could argue this is the most important thing to get right in climate models because very small increments in radiation matter, greenhouse gas forcing, climate change, et cetera. And then all the different components we can see there. Microphysics. So what's happening right at the smallest levels, determining condensation, freezing, all individual processes, Bergeron process, et cetera, precipitation, intensity. And so you could argue weather forecast models are more concerned with microphysics than they would be with radiation. Aerosols, over the last 10, 15 years, this has really come to the fore in terms of its importance, in particular interacting with all other processes. And then surface exchange, energy, water, momentum. How do we deal with the way the atmosphere, physically, the atmosphere interacts with the surface? So I mentioned it very briefly. Scales, I think you've been looking at models of various resolutions throughout the week, but in terms of what I'm thinking about here is how are we applying the physics on these climate model scales. So, we're of order 100 kilometers there in terms of horizontal, and then the time step currently is around 30 minutes, so 18 seconds. So that's where we sit at the very highest resolved scales. And even as dynamicists, that green shaded area is probably too far to the bottom left anyway in terms of resolved scales. But just to emphasize, I'm sure you all appreciate this, that when we're talking about higher and higher resolution models, I think this is just about where SCREAM and some recent high resolution versions of CESM sit. And so we can see we start to obviously resolve more processes. And the question of how to move the physics between the red and the blue is somewhat open, I guess. Just reiterating scales and what we're trying to do. So this is, you can see an island off the coast of South America there, and just up here, this point is terrible. Just up here is a little island called Selkirk Island. And that's around 8 kilometers. And it's obviously setting up some wake turbulence within this semi-permanent boundary layer stratiform clouds. But then, you just got to contrast that with this is the grid box that we deal with in a CMIP model, essentially. So there's a lot of information in there, and the question is, can we deal with that, turbulence-wise, radiatively-wise, precipitation-wise, potentially. Another quick example is, Midwest here. And, I'm sure this might happen today. Some of these, localized, intense storm events. And again, that's around 30 kilometers now. And then just putting on top, that's our grid box. I think we may have chance. But there's also issues that you may, give rise to, if you're close to resolving, you may give rise to very intense, very large grid box events as well. So that's kind of on the flip side of the intensity maybe. So, keep this general. So just to say what is the aim of parameterization? And the aim is to represent the impact of subgrid scale, unresolved processes on the resolved scale. So the information that's happening below the scale of physical processes are operating at below that scale. What are the relationships we can build in order to construct faithful responses of individual physical parameterizations to changes in that large scale? There's a few considerations here. So we try to use basic physics, laws of thermodynamics, etc., conservation laws in terms of constructing these relationships. We also use empirical formulations, microphysics, for example. Ice microphysics in particular, we use observational relationships to determine rate constants, etc. And I'm sure you talked about this, but just to emphasize, everything is assumed as a plane parallel approximation. So shallow atmosphere, we're looking at a column all the time. Radiation doesn't come in through the side of the column. It only comes in and via the angle of declination, gradually decreasing into the top of the column. So that's just to orient you like that. There is little retention of subgrid information across time. So if you say, this is not true, it was true in the past, and it's not quite true in the CAM6, but it's important to note that you can frequently determine all this subgrid scale information of which you construct, the tendencies that occur on the mean, but then you throw that information away, and then you reconstruct it in the next time step, which is obviously different to the dynamics. That is not, like I say, I'll say later, Club does retain some information. And again, distinguishing us from predominantly the weather world is that we're time splitting, so serial processes, tendency to process versus all processes at the same time, which is more of a short time step weather forecast way of doing that. And there's challenges with this, of course. In many cases, there's no explicit formulation based on first principle. It's possible. There's just non-linearities at these subgrid scales that cannot be formulated in terms of large-scale variables. And then this is also coupled with observational uncertainty. If you have these observationally based parameterizations, how appropriate are they for everywhere in the world, which they have to be? And then, just there's insufficient information. I mean, the simplest way you can construct, I always like to show a parameterization, and people are familiar with this. This is the vertical eddy transport of some quantity chi, so the mean of W prime chi prime. That's unresolved subgrid scale information. What are these eddies doing below a mean Reynolds averaged scale? And you can construct that as a simple down gradient flux based on some diffusivity, which is determined from maybe stability, but essentially some one-dimensional gradient dependent tendency. So it's very simple. But in all of this, of course, it's very much more less satisfying than the dynamical kind of formulations, and I always like to show this. This is essentially what the physical developers do, and like slaughtering these PDEs with the model. So, okay, so first thing was turbulence and clouds. Pretty plots here, of course, and there's like very much broad range of scales and related to clouds, condensation, assumed turbulence. And so the question is, how have we, at least traditionally, represented these phenomena in models? And so it has traditionally been these three-pronged kind of representations: stratiform, resolved, large scale, macrophysics, all those are kind of synonymous. And then, shallow clouds, smaller scale, smaller vertical extent, and deep convective clouds, somewhat larger, presumably, and then obviously deep and precipitating. And the bottom line before I say anything is the discontinuity amongst these is very obvious, not in terms of how they're all kind of related. You go out here this afternoon or maybe right now, and it's like shallow to deep, to more organized, and everyone recognizes that. We'll talk more about that later. But the assumptions that go into these three are inconsistent. They're different, and so the expectation that you would get continuity is off the table basically. And the goal of this, of course, is to think about what are we trying to predict, diagnose, and so the extent, of course, horizontal and vertical. Given we have a fractional grid box, horizontal will be 10%, 20%. Vertical is do we occupy a number of co-located levels? Are there clear levels in between? We need to think about phase change, vapor, liquid, ice. The total water content, radiation depends on this. And then in some cases, internal dynamics, but updraft vertical velocity, so downdrafts. And this is a way to do it, and as Isla pointed out, we're retaining some of these simplified ways to do it. This is CAM4, and actually before CAM4. And essentially, the challenge of, like you say, with what large-scale state, how that evolves, when does cloudiness form, and how does it evolve with changes in that state? Let's say relative humidity, of course. And then, cloud at 100 kilometer scale, cloud does not exist at 0%, and then suddenly it exists once you get to 100%. Of course, that's not realistic. And so the idea is that there are formulations with which you can transition the cloud fraction from, let's just say, some critical value where we start to form cloud all the way out to 100%. And you could just say just varies linearly. So as the relative humidity goes up, and the cloud fraction goes up. But that was many decades ago, and this was obviously seen as too simplified. But then you can fit functional forms where you increase relative humidity slightly, and you only get small changes, and then there's some threshold. And clearly, these are somewhat statistical and observationally kind of derived to a certain extent. But that's a simple representation of stratiform. If we were to think about shallow and deep, again, it helps us to kind of look back a little bit, I think, because the examples are easier. So for each of these, as I mentioned before, you're exploiting common conservation properties. For example, we're parameterizing the consequence of vertical displacements of air parcels, stability. Clearly, air parcels are rising, they're stopping, or they're rising to the top of the troposphere and precipitating. So this stability information is really important. And information about saturation. When it's unsaturated, conservation laws, like I say, allow you to dictate that it would follow a dry adiabat, conserving dry static energy. But then once they become saturated, cloud forms, then you are able to exploit the fact that they probably do follow something like a moist adiabat in the vertical. We won't go into this too much, but basically scales, we're all aware of this, and this is the general paradigm, is you don't get much positive buoyancy, cooling mainly because there's not so much latent heating or precipitation, and generally a source. So shallow convection generally injects moisture into the lower troposphere, which deep convection can exploit, of course. And then small clouds. And then, kind of on the flip, for deep, hundreds to tens of kilometers, we're trying to represent deep instability, deep heating, precipitation, and generally a sink of water vapor. Definitely in the model, it just obviously it's raining quite a lot in the tropics and here in the in summertime, and so lose a lot of vapor because of that. And also the scale of the clouds are very wide. Not a surprise. A couple examples across the models. CAM5 here was what was used was actually a continuous model from boundary layer through to cumulus representation. So this is the UW scheme that was put in a few years ago. And essentially that enabled the stability calculations from the boundary layer to inform the convective inhibition, CIN, this in, and then how that either restricted or enhanced shallow convection. So it's just an example of, controlling factors, convective inhibition, turbulent kinetic energy from the boundary layer, and how that was, and then used to understand the depth of convection via entrainment and detrainment. These are key factors for shallow deep clouds. What we have right now, for a long time, kept me in a job, CAM3, through to even CAM7, hopefully gone by CAM8. So this is, a few schemes are based on this quantity convective variable potential energy. So this is kind of some theoretical quantity. if you're exploiting those two properties that I said previously, which is dry static energy of a parcel when it's ascending unsaturated, and then on the flip side, moist static energy when it becomes saturated. So essentially, you can quantify a certain kind of energy that the deep convection can utilize, and that is used as both as a triggering mechanism, but also as a mechanism for amplitude and convective cloud top. So it's pretty simple, but it is very effective and stable. That's why it's worked pretty well for a long time. It's important to note that in these cases, which is probably one of the biggest shortcomings of CAM7, in my opinion, so write that down, we're diagnosing very simple cloud fractions, and the microphysics relationships are very simple. This is only true, obviously, for the deep convection in CAM7. That's a big problem when you think about the importance of microphysics in the most intense precipitation, which is deep convection. All right, so that's separation, somewhat not relevant to what we're doing right now, but now I'm going to talk about, can we do something more consistent across cloud types? So this is something that is in CAM6 and it will be in CAM7. So essentially, this is just for Isla, Scotland. And this is to demonstrate, cloud continuums in different regions. If you look, there is not distinct, within a grid box, for example, distinct changes from one cloud type to another. It's just arbitrary, but you move boxes around, you can see that there are transitions in a lot of these places, which for the most part are pretty smooth. So in terms of exploiting that, there's a scheme that was developed by Vince Larson, and it was intended to have much more consistency and seamless-ish in the way it's put in right now across these different cloud types. So essentially, stratiform through the shallow, through the deep, and actually upper tropospheric stratiform clouds as well. The attempt is to distinguish that in an eddy kinetic energy framework. So trying to solve the eddy kinetic energy evolution of the system. So turbulence, essentially, yeah. And the way we do it right now is we only currently do it across the non-deep convective cloud types. So they kind of subsume the shallow type into this representation in cloud layers unified by binomials, remember that. And one, as I've written here, one advantage of that is you can then bring in the shallow convection into a more consistent microphysics framework, which I'll talk about later. Deep lies outside it currently, but the plan may be either, experiments have been done with the whole range of cloud types within Club. So the idea is you solve the eddy kinetic energy equation, and this requires you, in the form that it's used in the model, is to solve 3 first-order means of fields, dynamic, thermodynamic, and water fields, 6 second-order, so variances and vertical eddy covariances, and then 1/3 order. So that's the vertical velocity, the prime, so the skewness of the vertical velocity. Club is tricky to explain in just a few slides. I always have to go back and try and convince myself I know something about it. But essentially, we have an eddy kinetic formulation. And so we can, in the basic sense, we can say, how does, in this case, a thermodynamic variable, theta L, conserved variable, how does that evolve with reference to turbulence that you would determine if you Reynolds average this? And one quantity here is how does the vertical eddy flux of temperature gradient, how is that calculated in reference to all the potential source terms that you can have? So if you break the vertical eddy flux, this is a bit of a not very crisp equation, but there are a number of terms associated with this that relate to, again, other first-order terms, other second-order terms, and related to real processes. So, buoyancy production, for example. If you have buoyancy, they get more turbulence. And turbulence advection, if you move it up, then you get more turbulence, simple as that. So that, this is pretty straightforward in terms of, writing out equations. The devil in the detail comes in. How does these subgrid scale variations, what are the shape of those and the nature of those in a grid box? And so the cool thing that Vince did was essentially to say, well, you can integrate the domains associated with these, vertical velocity q and theta primed and their phase domains. And I don't want to go into too much detail because I don't know it myself particularly, but it comes down to how do you describe the distribution of these quantities that you then can solve to determine the full TKE evolution. And the bottom line is, if you use these double Gaussian in these particular phase space regimes, 2 double Gaussians. And so, as an example, I think hopefully to illustrate, you're saying in this particular case, let's say this is a temperature variable on the left-hand side. So this is cold to warm, and then a vertical velocity variable on the bottom. Descent is to the left, ascent is to the right. So you could say in this grid box, if you determine that the distribution are described by those 2 PDFs, you have, a regime that spans a few temperatures, quite a few temperatures, and a few regions of ascent. So the variation, your broad PDF in ascent and temperature. And you could say, well, maybe that represents cumulus, because that's, there are the variance associated with cloud and temperature and vertical velocity is broad. But then, this particular region here, which is a much more confined region in both temperature and vertical velocity, you could say, well, maybe that's a much more continuous, homogeneous environment, so that's stratocumulus. So hopefully that illustrated that, this is the information that you kind of provide to the whole solution cycle, but also you get out in terms of understanding things like cloudiness. This is one example here. If you now kind of compare the water variable with the temperature variable, and of course, at some point in this line, there is saturation if you have more water. And given this PDF, this is kind of can tell you the fractional cloudiness if you think about it. If we had a single point value here, both in this side of the cloudy line, then you would just say, well, it's clear. But this allows you to say that this PDF actually extends into the cloudy portion, and that is where you can derive a cloud fraction. So hopefully that explains the benefits of using something like Club to do this span of cloud types in the model and get some more informative subgrid variability information. Okay, microphysics. So talk about cloud turbulence, and then what's happening in the development of clouds, microphysics that we can parameterize. So this is this very Hugh Morrison came up with this very nice impossible gram or whatever you want to call it of cloud processes, and it's something you recognize probably, a deposition entrainment, something you might not recognize, but essentially it is very complex, related to particle and size droplet distributions, ice and liquid processes, detrainment, entrainment, precipitation. So I mean, yeah, I'm not telling you something you don't really know, but I want to emphasize this is quite a complex problem. The way it is done, actually, just a sec. So yeah, just to reiterate, size distribution shapes that we have to consider, and then this, distribution and transformation of condensed species. We have to understand and implement rate constants for all these. They're very small scale processes, and a lot of these rate constants come from observational campaigns. They come from LES or DNS type modeling, or in some sense, some theoretical considerations. But they're very challenging to do in a very large scale model. So, and it is quite sensitive to a lot of these rate constants. I mean, once I show you another impossible gram. Once you can imagine that very fast processes are acting on ice or liquid, and they're potentially all going in very, very opposite directions, like evaporation and then Bergeron process, recondensation. And so in a model that time steps in 1800 seconds, 30 minutes, one could imagine that some of these fast rate constants would just evaporate out cloud or rain it all out. So this is more than any process, I think, that the time frame of this is really, of the real process, is really hampered by the short time scales that we use in the model for a number of reasons. We can't run 1 minute time steps, so we have to compromise it, 1800. And again, just to emphasize, this is non-deep convection. So everything we do on the condensation side, cloud side, apart from deconvection, is microphysics. The version we use, and we've used progressively more complex, comprehensive versions, is the Puma's version, parameterization for, oh God, microphysics has got across scales. Previous was this and Morrison-Gelman version, but this is the essence of what we have in the scheme. So essentially, you have a number of water quantities. Initially we just had cloud droplets, cloud ice, and water vapor that are predicted. So these are predicted based on a lot of these processes that I just talked about. And of course, these are advected species. So obviously the trace advection comes into play, moving these all around also. We originally had diagnostic rain and snow. So when we felt that particles were big enough, we just said that's rain, and we did something kind of different. We didn't prognose that. Similarly with snow. Now we do a much better job of that. One thing will prompt what I'll talk about next. Oh, 9:30, good. Is again, aerosols have been increasingly a more important aspect of the model, everyone's model essentially, and it's the interaction with, probably the primary one is the interaction with clouds. So aerosols interact with clouds and they determine number concentration, which is particle size. They can also determine the radiative effects of that. And so here, what I'll talk about in the next kind of physics set is the fact that these aerosol number really play into how the prognostic cloud droplets and the cloud ice are distributed in particular into the mass and number concentration. Also to consider is, although the convection does not have in its own formulation a complex microphysics, it is able to detrain some aspects of the liquid into the microphysics scheme here, and you assign it some essentially some mass and number concentration. So it's it's complex, and really it comes down to really two big processes, which is order conversion, which is basically when are drops heavy enough to fall as rainfall. I mean that's a key process, and as snow particles as well, and accretion. Just how are these related to the mass and the number concentration? Just essentially how do they fall through each other and they grow. And so these are, like I say, order conversion is related to, both the mass and number concentration, and then accretion is related to two properties of the number of the mass. So that's it in a nutshell. A little complicated, but super important process. Going straight to aerosols, like I say, I think it's great if I just read this out as a nice one. So atmospheric carbonaceous aerosols, just aerosols in general, play an important role in the climate system by influencing the Earth's radiation budget, modifying the cloud properties. Despite their representations, large-scale cloud models are still crude, which can influence model simulation burden, lifetime, physical, chemical, and optical properties. So there you go. That's the kind of things we have to determine the evolution of burden, lifetime, and particularly optical properties. And this is just a standard off-the-shelf diagram that just illustrates the importance. Aerosols in terms of emissions, fire emissions, dust, these are all considered in the model. Sea salt, sulfates, et cetera, and then all the radiative aspects of it, clear sky radiative, but also the cloud interaction aspects of it also. So it's pretty complicated, and it's almost impossible to be too complicated, according to the aerosol scientists. So what do we do? So we have something that's called the modal aerosol model. So I'll explain that. So what is a modal aerosol model? So essentially there are, four ways of, there's probably more, but four ways of understanding of different levels of complexity. Like I say, it's never too complex. But essentially you could just, treat these aerosols as a, mass-only quantity advected around. You just do external processing of it related to temperature, humidity. There's no internal, as in internal to all the aerosol distributions. And we have done that. CAM4 does this. So that's half of why CAM4 is cheap, because we don't have all these, we tend to prescribe, and so we don't have all the overhead of advecting these species. You can go complicated, like these multiple bin sizes, they look like histograms, and there's a lot of movement of aerosols from particular bins back and forth. But it's expensive, and it tends to be just used for the really like short-term, really intensely local processes. And then there's more of the process level, which is the Lagrangian type thing. So this modal approach, this is, I think, a nice graphic of that. So essentially, we have a distribution of particles. This is log, a normal distribution. And the idea is, instead of representing each number of species, let's say dust and sea salts, sulfates separately as a separate, you kind of gather them into different bins, if you like. And there's kind of 4 recognized bins. This is kind of a really tiny formation type bin, which we don't have in this version. MAM7 has it. So essentially, each of these bins are thought to have distinct properties related to water affinity and how they grow and how they deposit, how they wet deposit with rainfall. And so you can collect these and treat the essentially internal, that's why it says internal per mode, the internal chemistry, which is very simple. It's the simplest chemistry we do, essentially. And then treat them all, treat all the chemistry within internal to each mode. And then you break all the individual aerosol types out to advect them all around until the next time step. And here you can see essentially what that looks like. So these are the 3 modes that essentially correspond to these 3 types of modes, the coarse, accumulation, akin. We changed this recently, a few years ago, that we have this extra mode that allows black carbon to exist at high latitude. But essentially, you see here all your popular, well-known aerosol types, but they're all just buried with certain commonality into these modes to be processed. And like I say, then you can break out individually once you've done the chemical processing, which I'm not too familiar with, but it relates to this basically, condensation, coagulation, et cetera. And then understand like what has happened to sea salt, essentially. So it's a little opaque, but that's, I don't usually talk about aerosols. I'll leave that to someone else. Next thing is radiation. This is really complicated. There are very few people in the world that can really talk about radiation schemes, and I'm not one of them. No, I mean, basically, I mean, this is, people may have seen this. This is like the estimated energy flows around the system. The black lines, the black numbers are basically best guesses at this time, 2011, of the incoming radiation and outgoing radiation on the long wave side, and also on the long wave side here, clouds are involved, and on the short wave side. And I certainly do not want you to digest all these numbers. The numbers in and of themselves, they're estimates from a number of sources. They're a little old right now. Most of them are reanalysis, if you're familiar with reanalysis. So all of these estimates of all of these, different components. And clearly, there's not that great agreement in the mean. Some of them are, when you average them all, they're all a bit too low or high. But the essence of this, just to demonstrate how important radiation is that, the global signal for, global warming at this point is 1. Maybe it's 2 watts in terms of when you add all the long wave contributions, short wave contributions, and then you say, what is the net increase if we increase CO2, for example, by a factor of 20%. And it's just to illustrate, the estimates vary from -11 to +10. I mean, that just goes to show that the importance of radiation, the residual that is required to get a climate that is either balanced or evolves correctly over the 20th century is really challenging. So, I just wanted to emphasize that. Try and move along faster. And so what does radiation do? It's no surprise I'm going to say this, but essentially the radiation scheme is, meant to understand how the shortwave radiation spectra comes in through the different wavelengths, shortwave, incoming radiation, and then determine how that is lost in terms of outgrowth emission radiation. Okay, so that's pretty simple, order one problem. Obviously there are devils in the details. If you think about how the atmosphere responds to shortwave and long-wave radiation, these are different long-wave absorbers, all the familiar ones, and this is total absorption. And so, there are a lot of bands here and like a lot of detail, and that don't seem that systematic, I guess. And the important region here is the atmospheric window region, and that's being in the climate change signal, it's being eaten away very gradually to kind of to be a greater spectral absorbing region. So to capture this is really the challenge of what radiation has to do, and that's without talking about clouds, aerosols. So it has a lot to do, but it's complex in terms of those bands. And so this essentially is showing. This essentially is showing what's the absorption of water here, the mass absorption over these wavelengths essentially, and there's a ton of variability, 10 to the 4, 10,000 down to 0, or whatever, 0.1. So it's huge, and even within you can't quite see it, but there's a lot of pretty big variation. So there's lots of variation. The question is, how do you? This is like very accurate line by line modeling, very expensive, and we can't do that. So we have the scheme, rapid radiation transport model, and various evolutions up to this kind of parallel version. And what is done in terms of what makes it rapid, I think, is you can reorder all these most important, reorder and gather all the most important radiative bands, and then to redo this, calculation within the scheme. And it improves accuracy and improves speed, and doesn't lose too much accuracy, but it improves speed significantly. And this is called the K distribution band model, and there are some. You can make it even better by saying certain levels are correlated with each other. And so, radiation it goes conceptually and implementation. There's a big change. There's a big jump from conception to implementation. But basically, this has allowed us to make radiation not like this big kahuna that it had always been, probably in Cam 3 and before, in terms of cost. All right, let's just move along. So this is like the last set. That is just a few bullet points. So basically, atmospheric surface interactions, probably maybe the most important is essentially the lower boundary level interaction with the near surface, land ice, ocean, and how that exchanges momentum, latent heat flux, and sensible heat flux. And this is based on a very established but very old, 70-year-old theory, mononomic of similarity. So this is essentially, relates the certain kind of diffusivity, but it's not simply like that. It relates to stability dependence. It's neutral calculations in terms of stability, but then it's modified based on stability, instability, and stability. And that dictates, So just to emphasize these boundary layers. And this is over a city and over the ocean, essentially the low-level wind and structure of the near-surface atmosphere changes with reference to these stability functions. So that is used everywhere, and it's applied to grid mean over ocean and ice. Over land, they have all these different kind of functional types, and it's applied based on the roughness of all these different land types. It's applied evenly, applied specifically to each of those, because it's a little bit more complex. Another process, turbulent mountain stress, essentially. So this is another kind of surface stress. So it's the flow is responding to the presence of certain scaled structures in the mountains over topography. So it's an additional stress on the momentum, essentially. So it's slowing the low-level winds down, and also in reference to how the orography is oriented. So north-south versus east-west, etc. That's another drag, potential drag on the low atmosphere. And finally, another drag, if you like. This is a bit of a draggy slide. We have this, as we've kind of really recently, not discovered, maybe rediscovered, but like it's a pretty darn important process for determining momentum fluxes, divergence, convergence, flux divergence, flux convergence in the atmosphere all the way up to the stratosphere. And so these kind of forcings are developed, in reference to mountains, but also deconvection and frontal systems. And like I said, we've seen some big impacts in this high top version of the model, and also the importance that relates to things like the quasi-biennial oscillation, which is in the stratosphere. That's my thing. But essentially, this is tricky because thermodynamic conservation properties are pretty well, are easy to enforce. Momentum conservation it is much more difficult to enforce and understand in these formulations. So that's it for everything. That's not everything, but those majority things. And this is just my everythingogram, which essentially tries to illustrate that a lot of these things are related, and maybe the difficulty is not necessarily that we put good physics schemes in the model. Hopefully we do. The challenge comes from how did they interact to do the science that we want to do. Maybe I'll just spend 4 more minutes, a couple of these slides. One complicating factor that is different maybe from a high resolution, even a high resolution version of CAM, if we configure it that way, or WRF or MPAS, is fractional cloudiness. So, in the model, we determine, based on, mostly on club, but the deep convection as well, a particular fractional cloudiness. Each of this cloudiness extends the vertical extent of a level. So these are like 3 levels adjacent. And so, certain cases are a little ambiguous in terms of how you understand cloud layers overlay each other. This one, for example, if you have a cloudiness here, 0.6, and there's nothing in the middle, and then 1, kind of doesn't matter where you put that 0.6 in the left or right. You're always going to fall through clear and then hit cloudy air. But if you have that 0.6 and you're overlying something that's 0.3, then you're like, well, I've got my drops and my radiation. If it's maximally overlapped like this, my drop falls here, it'll evaporate here, but it'll fall through cloud again, so you'll double your drops. For the drops again, if I was to minimally overlap them, then 0.6 is completely overlapped over clear air, and then you would lose your drop. It would completely evaporate. And this is just that, there are details in this that are important, but I think it's just to illustrate this cloud overlap issue in fractional model setups is difficult. And microphysics, for example, has worked quite hard in the most recent version to make that a much more seamless transition to something that exists on the right-hand side, which of course is high resolution, it's cloudy or it's not cloudy, it's clear or it's not clear. So that's unambiguous. It's just that a lot of sensitivity can come from how you determine these levels are overlapped or not overlapped. What happens if there's a distance between them? Do you kind of decorrelate them? And so it can have a worryingly large impact, let's just say. You know what? I am just too many. I'm going to skip to the last one. There's the last slide. So this is kind of a little bit similar to what Isla emphasized, which is we have, this is I put this together one time. It's the evolution of the physics and the dynamics at the bottom in the model for 25 years, 27 years, and just to emphasize that the green I think is new from the previous version, mostly new, significantly new. Let's say that. So it's just to emphasize, in climate models, you tend to have fewer options. Slower turnover of the physics, but we work really hard to get a good model that is bulletproof for CMIP. There's no doubt about it. We work really hard to do that. And, this just to distinguish ourselves from forecast models that have many different options, have a lot of you know, rapid turnover development of physics, and, you know, probably works great. You work on it for a year, works great over the Midwest, you know, but may not work so well elsewhere. So we put a lot of effort into making them work as well as we can in global long-term simulations. And yeah, I think, yeah, so CAM 4 and CAM 6 will remain available. I think Isla's, is she gone? Yeah, I think they'll remain available. So, and much cheaper. And that's why I talked about it a little bit, just to emphasize that there's some physics in there. There's some ways it's easier to understand, but is more basic, but much quicker. So I think it's great that you will, as dynamicists, you'll have that ability to really go with a much cheaper model to do the science you want to do. All right, thanks.
Yes.
How does CAM 6 and CAM 7 deal with lightning?
I mean, there is some chemistry application of lightning, I believe. I don't think we don't deal with electrification in a prognostic sense in clouds. Like the movement, one can imagine, you know, microphysical movements. I mean, one of the problems, as I've mentioned a few times, was we don't have that advanced microphysics in deep convection, where you could maybe, you know, include something from that. But you know, the chemists have come up with something. It's probably extremely basic.
Well, like, I know in CAM 5, I think it produced NO.
Right.
But does it couple with the chemistry model, or is it just parameterized on the fly where it's this much NO just being added into the system?
I mean, the full chemistry model, so the only chemistry really here is what I described for the moving results. But they run a much more augmented chemistry version that, yeah, I'm speaking outside my depth here a little bit, but I know that they were, for the NOx, they were very excited to be able to represent that.
And I think Mary works with the Lightning code, and they pick it off of the cloud top from the ZM scheme. So it's some statistical function of the cloud top from the deep convection scheme, and it produces NOx. So it only does something when you have full chemistry on it.
Thank you so much. I'm sorry that I want to ask about what seems to be your two favorite topics, aerosols and radiation. With this kind of simplified aerosol scheme, does hygroscopicity get incorporated into the radiation?
I mean, well, the optical properties that would induce, I think, get pulled into the radiation. It depends if it would be a gross sense, how would it affect the optical properties, I think. Do you think if it's like a water film? Yeah. No. Yeah. But I don't know. I must confess I don't know. Sorry.
I'm curious about, does the cloud parameterization consider lifetime of cloud?
Which?
Lifetime of cloud.
Was that club, you say?
Cloud.
Club. Was it club? Sorry, the club parameterization?
Lifetime of clouds?
Yeah.
In club?
Yeah, is it altitude dependent or independent?
I'm not quite sure. You mean, is it independent of time or?
Since someone pointed out that the lifetime of cloud is much longer in a higher altitude. So I'm curious about, is the design of the cloud parameterization here
Right.
also?
Got it, sorry. So club has information about subgrid scale information that is retained over time. So, and it depends on how, the process related to the cloud, it changes those moments. Like I said, the information is actually retained, so you're not reconstructing every time, the cloud properties. Now, if it's super saturated and there's no rainfall, it will exist over time because the tendencies related to precipitation or evaporation don't change. But it's just, there's two things. There's the information about subgrid scale cloud properties is retained, but also, it just depends on what's it being exposed to in terms of larger droplets and precip falls out and then the cloud disappears, or is it evaporation and then the cloud disappears? They are all kind of associated timescales with it. So, not not directly, but I think just generally through the processes, they themselves have timescales associated with them.
That's a place where you want a non-diffusive convection scheme for these clouds that
Yeah.
sit around for a
Not
week or two, where the dichrome might matter. Okay, go ahead.
Thank you, Rich, for the nice talk. I'm curious to know, like, with the deep convection scheme, the ZM scheme, I noticed that there is some change with time, like ZM, some mode 1,
Right.
some mode 2. Like, what's actually changing?
So there's 2 or 3 changes. The big change really was when we went from CAM 3 to CAM 4, that calculation that I showed of the cape profile essentially, was essentially assuming that convective parcels ascended but never entrained. So you've got very on-off convection. It's like, oh yeah, I'm not entraining, so I'm really seeing a very properties near the surface that makes me very unstable, then very stable, then very unstable. Whereas if you allow that parcel to entrain the environmental layer a little bit, you can kind of get this moderation. And the benefit of that is you increase sensitivity to tropospheric humidity. That was the key thing. And that helped a lot of phenomena. The NGO, for example, and Mann-June oscillation, dinocycle precipitation, that helped a lot. And so that was the big change, and changed a lot. And that was between 3 and 4, CAM 3, CAM 4, CCSM 2. Yeah, we can talk.
Could you talk a little bit about the role of these convection schemes in the newer non-hydrostatic cores relative to the hydrostatic dynamics previously?
You know, in terms of the role of the convection, I don't think there's 2 ways to look at it. Like, maybe is it responding to the explicit non-hydrostatic dynamics? No, really. I don't think convection. It doesn't care. But how does it respond when resolutions get finer? Then that's one of the biggest kind of conundrums of what do you do between everything I've said and 3 kilometers in terms of deconvection. And there's a whole kind of cottage industry of trying to understand how to just turn it off, or do you moderate it, dribble it in, and all these things, yeah. So unless Peter wants to correct me, I don't think there's any explicit response to the fact that you're running non-hydrostatic and hydrostatic dynamics. It's more to do with the resolution.
Go ahead.
So I want to ask about precipitation or precipitation rate. How well are we doing in CAM 6 as opposed to CAM 7?
Precipitation rate. You know, I can only, maybe Adam wants to say something too, but like, I think in general, we call it the drizzle problem. So it's around, I remember, 5 to 10 millimeters per day. There tends to be a lot of kind of background drizzle from the convection scheme, which we've had problems with a lot. And so but on the flip side, we struggle to get the most intense precipitation rates. So we kind of have this tilted spectra of precipitation. And that's always a challenge with large grid scale models, I think. But specifically on the way cloud is precipitating, I'm not sure. I don't know.
I mean, I would just say that going from CAM 6 to CAM 7, we're increasing the vertical resolution for the low top from 32 levels to 58 levels. And what we've seen is that tends to produce more grid scale condensation in the extreme precipitation rates. So we tend to get larger extremes precipitation rates in CAM 7.
Okay, Christiane?
Yeah, I think that's an open-ended question. Can you talk about time step sensitivity or also spatial scale sensitivity?
Well,
all right, if you have it. Just click away the window.
Yeah, okay. These are all good examples, but I like them. You know, time step sensitivity on the physics, I think with the physics, it's not that bad, I don't think. In my experience, you know, this is an example there of like long wave heating and the microphysical heating probably from a single column model. So this is, I don't know about the dynamics, of course, yet. It's never been that bad. Now, just bottom right there, just to reiterate my point about the convection, there is significant convective sensitivity in things like cloud fraction and deconvection when you go across those resolutions. So that's, now this one here is a little bit complicated, but essentially it's saying, when we first started doing the resolutions that Adam was talking about, increasing resolution all the way up to 256 levels is huge. In some things, this is the tendency of convective heating in the lowest model level. And we're getting down to 60 Kelvin per day there at a single time step. So there are sensitivities. I'm not sure whether these now are the biggest sensitivities, but I think the time step, I don't have that much experience with the time step sensitivities, but maybe others.
Last question, real quick. I think I was looking at you, Thomas.
Yeah, sorry. From a physics point of view, what are you thinking about in terms of physics dynamics coupling? What are the issues that you see? What are you working on?
That's more on Peter's.
I gave a 1-hour talk on it.
I know. I wanted to see the physics perspective, not yours. Yeah.
But I'll answer the question. No.
Yeah, thanks for your talk. I wonder, could you tell more detail about shallow convection and deep convection? Because some figure out there is a competition and between the two different convection. So how do you balance them?
So here, I mean, I'll talk about Cam 6 and Cam 7, which is Club does, if you like, shallow and large scale continuously with one entity essentially. And then deep convection is separate. I mean, the challenge is though, like I said before, the approximations that go into these two ways of calculating are very different. And so there's no doubt that if there's, in terms of competition, if there's deep instability, deep convection is going to win because one small reason is it's a non-local scheme. So if something happens at the surface, it impacts every level at that time. Whereas Club kind of has to build up in time. There's no significant non-local impact of Club. So that's an example, I think. Significant instability in the vertical. The deep scheme will win every day, I think, because it can just respond. Even though Club may be seeing some of that instability, I don't think it is as nimble to respond in a non-local way. I'm sure there are other examples of how they're competing, but
yeah, thank you.
Okay, let's thank Rich again.
Have two 2-hour-long, well, 1-hour-long slots, so a 2-hour time block. We will break it up. So the speakers decided actually we have 2 speakers per time slot. Yeah, so we actually will hear from 4 people, starting with Cecile Hanet and Brian Medeiros here from NCAR, here in the Climate and Global Dynamics division, and they will actually hit upon, and that really is a nice follow-on to Richard's talk. What if you have your model, what now? And the next question is, once you have your model together, it's how to tune it to make it correct or as correct as possible. Correct may be the wrong word, you have to make it an accurate model. And so we will hear from Cecile and Brian how to tune both the physical model, the CSM model in this case, and also machine learning models. So take it away. Okay, thank you so much.
Very impressed by the crowd because I have been really involved in the CSM tutorial, and usually it takes people more than 5 minutes to come here, and I time you 1 minute. I'm amazed. Yeah, I have a bell too, but it's not helping. Then today we are going to bring you into the CSM factory, and we are going to talk about model development and the tuning that we are doing during model development. This is the outline of the talk. Then first we will talk a little bit about the timeline when we built the version of CSM, CSM2. Then we will talk about the art of tuning a model. Then I will give you a little model development tale, story that what can go wrong when you do model development and tuning. And then Brian here will talk about the tuning during the machine learning era, because I know nothing about it. Then basically you have seen this on the slide of Dave Lawrence, and this is the version of the model, and basically I want to show the timeline to build this coupler with all these different components. Then basically I'm going to take as an example CSM2, and it gives you an idea of the time scale. We started to build CSM2 in 2010. And we build all the different components of CSM2. Every working group, we just finished CSM1 in 2010, and then as soon as finished CSM1, we started to work for the next version of the model, and every working group was working on the version of the model. Then I'm the liaison for the atmospheric model. Then I'm going to take the atmospheric model as an example, but basically, what we were doing, we were focusing on aspects of the model that we wanted to improve, and we were looking at dynamical core resolution. Then we also look at the new physical parameterization in the model. And at the time, we did a lot of uncoupled simulation than just the atmospheric model, and we were analyzing all this simulation. And it was an effort, and we were doing this in the atmosphere, but the other working group were doing something similar for the other component. After this 5 years, we had components that were more or less ready, but then we started to put everything together. We started this in November 2015, and we had at the time a lot of meetings. We will meet like once or twice per week with everybody. When I say everybody, it's all the co-chair and all the liaison of CSM. We had over 300 couple configuration of CSM, of couple CSM, and we did thousands of simulated here and diagnostic. And at the end, CSM2 was released in June 2018. Then basically, this is a long-term between major release of the model. Then you see that here, for CSM2, it was an 8-year effort between when we started and when we released the model. We started to work on CSM3 right away in 2018, and we are expected it will be released really soon, but you are going to see that we have always issue at the end. And a lot of issue. Oh yeah, and also what I want to say, this is not, here I say we build a model and then we couple them together. There is a little bit of back and forwards between we build and then we start coupling. In CSM3, to try to avoid the surprise, we started even to try to couple version of the model earlier. And basically, along the way, we are doing the model tuning. Then I'm going to talk now about what I call the art of tuning. And basically, tuning the model, it's when you adjust parameter, what we call the tuning knob, to achieve the best agreement with observation. Then if you look at this definition, when I say adjusting tuning parameter, it's parameters that are weakly constrained by observation. I'm not going to tune Coriolis parameter or the gravity, but they are parameters that are not really well constrained. And an example that I'm taking here is the DCS, is the threshold diameter to convert cloud ice particle to snow. Then basically, what is this parameter? You see here the cirrus cloud over Boulder. Then they are made up of ice crystal, what we call the cloud ice, and they are at high altitude. And this is a representation in the model of the cirrus cloud. And you have ice crystal, and you have different diameter of the ice crystal. And basically, the DCS, it's going to be the threshold diameter. You decide on a diameter that if the crystals are bigger than this, they will just fall out of the cloud, and we say that the cloud ice convert to snow. Then this is an example of a tuning parameter. Then what's the impact of this tuning parameter on my simulation? Then on the left, I have a cloud with a smaller DCS. Then you see that you have less ice cloud because all the big ice crystal has fall off. And on the right, I have a larger DCS, and I have more ice cloud. Then what's the impact on the climate? Then it's going to have an impact on the infrared radiation that goes to space. Then if you have a smaller DCS, you will have more infrared radiation going to space than on the right side when you have more ice cloud. It has also some impact on the shortwave, but we will not talk about this here. Then now, what we want to do is to achieve best agreement with observation. And basically, this is here the Earth energy budget. And where is my DCS? Then it's going to have an impact on the infrared, the outgoing infrared radiation. Then here on the plot. Yeah, then this is also in the Earth budget, something that we are going to tune. It's the energy balance of the whole system, then what we call restom in the model. And basically, we want to have the top of the atmosphere radiative balance that should be very close to zero. Then why is it important to tune the atmosphere radiative balance? Then this is an example, a model that was not really well tuned. I have a radiative imbalance of about 1 watt after 18 years. Then what's going to happen? Any clue? If I leave the model like this and I run a long couple simulation, we are injecting it in the system. It's going to end up somewhere. The atmosphere has very low heat capacity, then the ocean is going to warm up. Then usually when we are going to run this, we cannot really run long before we have the oceanographer in our office asking that we reduce this imbalance because it screwed up the ocean. Then, then the top of the atmosphere should be near zero. It's a big tuning parameter that we do, but we have several tuning parameters to adjust this, but we have also as a target that we are looking when we are tuning, we are looking at a lot at the cloud forcing in the model. We are looking at the precipitation. We are looking at the INSO amplitude, the AMOC, and also the sea ice thickness and extent. Then it's not, we are looking at a bunch, and it's always hard to get everything right, then we have always to do compromise. And it brings us, like, we have some always dilemma when we do some tuning, because first there are a subjectivity of tuning target. Then when you do the tuning, you cannot get everything right, and you have always to sacrifice something, sometimes to sacrifice something to get something that you consider more important. The good news is that overall, the tuning has a fairly limited effect on the model skill themselves. And also dilemma is that if you want to do tuning for pre-industrial, or if you want to do tuning for present day, a different modeling center will choose different strategy here. Then us, we tune often our run in pre-industrial when we run the couple model, and we want to have, because we want to have radiative equilibrium. But as a modeling center, prefer to tune present day because it's where they have available observation. Also, there is a question, do you want to tune individual component? Then do you want to tune the atmosphere, or do you want to do your tuning in couple mode? Tuning in the individual component is really fast, especially, for example, if you're tuning in the land model, you can do a lot of run really, really fast. But the problem, there is no guarantee that the result will transfer to the couple model. And I'm going to show a few examples in the rest of this talk. Then often we do like some basic tuning in a standalone in the atmospheric model only, but then we do a lot of tuning after in couple. And the last thing is that even if it takes time to do the tuning, it's a very educative exercise because you are learning a lot when you are doing the tuning. Then now I want to show you a few examples that what can go wrong when you are starting to couple your model and you are doing your tuning. And I like to say that coupling, it's when I unleash the beast. Then basically when you are doing a standalone run, an EMIP run, then when we use sea surface temperature prescribe, then when you prescribe the sea surface temperature, the model cannot drift anywhere. Then you have a really well-behaved model and really nice. Once you start to couple everything, you put the full ocean, the full active ocean, and then you have couple bias and feedback, and you can have very quickly a runaway simulation. And I'm going to show you a few examples that happen during different versions of CSM, because history is always repeating, it seems. Then the first example I want to show you, I go back when we were doing Camp 5. It was for the CSM1 development. It was in 2009, and it was a while ago. And at the time, we were doing most of our tuning in EMIP mode. Then we were using prescribed FST. And we had introduced a lot of new parameterization in Camp 5, and we had really a perfect simulation. We were so proud. It was really beautiful. Then we put it in the couple model, and what happened, but very, very quickly, we had a very strong cooling in the North Pacific. And it was, you see here the SST arrow grow really quickly. And here it's a picture of Rich on the left. You see year 1, year 2, after 12 years, I have this major cold bias that developed on the North Pacific. And basically what was happening is that we have called the SST. Then because of this cold SST, I had more cloud in the North Pacific. Then because I had more cloud, I had even colder SST. Very quickly, the CI started to grow. And then we had even colder SST. And in no time, we had a running away simulation.
A new ice age.
Sorry?
A new ice age.
Yeah. And then what we had to done at the time, because we had really good cloud forcing in the North Pacific at the time, but we had to make them not as perfect to avoid this feedback that we had. Then it was the way that we solved this. Then at the time, we solved this issue. But then a little bit further, at the same time, we were trying to move from the finite volume dichrome to the spectral element dichrome in CSM1. And at the time, it's like we had learned nothing from our first experience with the North Pacific. We were still doing all our tuning with prescribed SST. And again, we had finite volume and the spectral element dichrome, they were producing very similar simulation. It was almost boring. Then we were very confident that nothing was going to happen. But then when we coupled the model, the SST, in black you have the SST time series in finite volume. It adjusts a little bit, but it's stabilized to some temperature. But then when we put with the spectral element, we were stabilizing like half a degree colder. And then this is here the global ocean temperature. Then you see that we were forming on the left, it's the FV, on the right, it's the spectral element dichrome. And you see that you were forming a warm layer around 500 meters, and then at the top it was cooling at the surface. And basically we had a problem, and we could not live with this. Then we did a lot of work to try to avoid this bias. And we look at what's different between the finite volume and the spectral element. And there was some difference in tuning parameter. The RH minel, it's something that affects the low cloud, mainly the airpan, it's something that affects the transition between low cloud and cumulus. We had also different in dust. We had difference in the grid, especially at high latitude. Then difference in the topography. We had a new software to generate the topography. We had also some mapping difference and some difference in the surface stress. Then all of this was fairly small difference, but we decided to test them one by one because we could not guess which one would matter. And can you guess? Who would? Any guess? You can. We didn't know. Then we try everything. I'm going to give you a little clue here. Then if you look at the zonal stress, the maximum, the south, it's on the right side, then the maximum of the zonal surface stress, it moved a little bit north when we move from the finite volume to the spectral element. And basically, this is this small shift that we saw that would not matter that created this runaway simulation. And basically, what was happening here, I'm looking at FV and SE compared to a simulation, a difference with the ocean only. And you see that you have difference in the wind stress curl at 50 south. The oceanographer will always put the south on. Yeah, I show you the first picture here. The south are on one side, now they're on the other side. Then because of this, it had an effect on the upwelling of cold water. You see that you have an anomaly around 50 south. And then it was carried over by the ocean circulation. Then you had cold SST that was advected north by the ocean circulation. And basically, it's because of the location of this small shift in the surface wind, then we had this runaway simulation. And basically, at the time, we could not solve this problem. We tried really to solve it, and we were not able to solve, and we end up not releasing CESM 1.2 with spectral element as the default. We kept it in finite volume because we were stuck. Interestingly, as a center at similar problem, they were seeing the same thing. For example, the GFDL model, they were moving from the Eulerian dichrome to the finite volume dichrome. And if you look here, they were having also this small shift in the maximum of the zonal wind stress. But in this case, it was helping. It was increasing our bias, but for them, it was reduced bias. Then, of course, when it's reduced, nobody worry about it. But sometimes you are really stuck and you cannot solve the problem, and you have to pick another strategy. The last thing that I want to talk about, it's the Labrador Sea issue. And then this is a big issue. It has been a big issue in CSM2, and it's now, again, a big issue in CSM3. But this is basically on the plot here, you see in CSM1, it's the observed ice thickness. It's the black line, the very thin black line that you see on the plot. And you see the sea ice extent was pretty good in CSM1. You see that the black line, it almost follows the black line. And this is how it looks in CSM2. Then the region in the box, it's the Labrador Sea, and you see that the Labrador Sea is ice cover. And for us, it was a showstopper. Then we start to do a lot of work to try to solve this issue. Why was this happening? Then basically in CSM1, we had some bias. The region near the Labrador Sea was too warm and too salty. But in CSM2, we had also bias, but it was the opposite direction. It was too cold and too fresh. And then because of too cold and too fresh, in this case, it was leading to the Labrador Sea freezing. But we had bias in both cases. But in the case of CSM1, the bias was helping us. In the CSM2, it was going against us. And basically, we end up with CSM stuck in boat for a long time. And it's why it took 3 years between the moment we start to couple the model and when we release it. And what was really distressing, here I show a few lines. This is the evolution of the sea ice thickness in the Labrador Sea. And you see that the sea ice was building in the then the bottom line, it's CSM1 and CSM1.5, and all the ones that are going crazy, it's CSM2 development. What was hard is that it could happen after 1 year, after 40 years, and sometimes even after 100 years. And it was very difficult to know when it was going to happen. And I want to report we have the same issue right now with CSM3, and we have a simulation that froze after over 200 years. Then it's very hard to say that we are very safe. We are safe at some point with a simulation. And then again, we did a lot of work trying to fix the issue, but it was we tried so many things. And I love the people here because they're so creative. They found like idea, and it's really nice. But it was a very robust feature in CSM2. Until we got lucky, the oceanographer put the estuary box model at the time, and indeed it helped us. Because when they include this model, they were having a bias compared to the control, the salinity. You see that they had a positive bias in this, but it was more salty and warmer near the Labrador Sea. And at the end, it really helped us avoiding the freeze in the Lab Sea. And I should say we are not the only model to have this. You have other models that have problem in the Labrador Sea freezing, but some center decide it's not a showstopper for them, but for us it has been a showstopper, and we have been struggling with this. I didn't add anything for CSM3, but we have same kind of issue right now, and we are working on it, and hopefully we can solve this soon. And basically, I hope I have convincing you that coupling, and when you do the tuning, it can be unleashing the beast. And I'm going to give the stage to Brian, but basically it's a summary of what I said. This is the timeline when we built CSM2 in 2 phases. It's a long effort. It took 8 years for CSM2, and it's very typical. We saw that tuning, it's achieving parameter, what we call the tuning knob, to achieve best agreement with observation. We saw that it involves choice in compromise, but we learn a lot about the model during tuning, then it's good. And then I give you 3 examples of what can go wrong when during the CSM development, when you start to do the coupling and the tuning. Then we're going to keep the question to the end. I want to say that all my cartoons, this is one that my son did, but all my cartoons were done by my husband and my son. And I call this non-artificial intelligence because in the next part we are going to use machine learning, and we will have animation, picture that maybe are created by ChatGPT. No, sorry, I'm leaving with.
Maybe thank Cecile. I would suggest that we hear Brian and then move over to the Q&A session.
All right, so that sets us up. I think that you can understand now that tuning the model is difficult, traumatic. So we might want to be thinking about what we can do to change the process to make it a little bit more efficient, to do things differently than we've been doing them for a long time. And this is one potential avenue that seems to be getting some traction, but we have to learn a lot about it. So I want to thank Linnea Hawkins for helping me put together these slides. She contributed a lot of the actual content of this presentation. I want to remind you so Cecile ended sort of with some challenges, but also with some optimism. I'm just going to focus on the challenges of what I'm going to call hand tuning. So it's a large number of parameters that you have to adjust as you're going through this. It's really slow the way we do it. We would basically change one thing at a time, run the model, analyze the results, get into a room and decide how to change the parameter again, or roll it back and change a different parameter. So it's a very slow iteration process. It's really complex, as Cecile has described, to understand what parameters are important, why they're important, and how to actually change them to make things better. And it's ambiguous, and so that's in a couple of ways. One is that it's difficult to choose the tuning targets and to make them objective so that you know when you're actually doing better than you were doing before or not. Things like INSO and things, I mean, these can be hard to do. But also, the way we've been doing tuning for all these years is really a kind of random walk. We're sort of like changing a parameter, seeing if it makes it better, change the next parameter, see if it makes it better, keep going, and you're finding your way through this very high-dimensional parameter space to a nice pocket of softness where you might be able to find a version of the model that you like. But that means that you're not exploring huge parts of the parameter space that might still be viable in terms of model configuration. So we'll talk about that. That's going to be important for the rest of these slides. So we should be thinking about how to more systematically explore this very high-dimensional parameter space. And so what I'm going to be talking about now is kind of going back a little bit in time, away from the coupling, away from the beast, and talking about tuning individual components for now, and then we can worry about coupling at the end. I think that is a big challenge. So we need to explore the sensitivity of the model through its parametric uncertainty by perturbing parameters. We need to generate a large ensemble of simulations with different sets of parameter values, and then analyze that and to identify sensitivities, and figure out which parameters are important, and then understand why they're important and how we might be able to move forward and make adjustments to make the model better. So for a long time, people have been doing this, and it's usually called a perturbed parameter ensemble or a perturbed physics ensemble. So it's a large set of simulations that each do some kind of perturbation to the tuning parameters of the model to produce a big ensemble of simulations that you can analyze. This has been done for many years, and lots of modeling groups have done it. We've done it recently with CAM6, so uncoupled version of CAM6. Trude Eidhammer has a paper describing this PPE. It has about 260 ensemble members, perturbing about 45-ish parameters or so. They're all listed in this table here. Not very attractively, but I tried. And then they did several kinds of analyses in that, but one of them is shown over on the right side of the figure, where the parameters are along the vertical, so the 45 parameters or so, and then along the horizontal in each row, in each column are a bunch of physical fields where they're basically looking at the correlation between the parameter variation and the geophysical field for global averages and then regional averages. And the brighter the colors, it means the stronger the correlation, which means in some sense those parameters are the important ones for that field and for that region. And they did other things, but that's one of the key results from this paper. They've been doing the same thing with CLM, the land model, for a long time. So Katie Dagan and Daniel Kennedy and Linnea Hawkins and others have been doing this. And they also start with a very large set of parameters, 30-some parameters in this case, and then they kind of narrow it down to a few parameters that they think are important and do a calibration that I'll describe in just a minute to arrive at a calibrated version of CLM, shown over there. So how do you do this calibration? Well, the main way to do it now in the last few years has emerged to build an emulator of some sort. And there's been kind of precursors to this for a long time. A lot of it was called uncertainty quantification for a long time, and now it's just kind of called model parameter estimation or parameter calibration. And so these emulators are statistical models that try to capture the parametric sensitivity of the model. So you map the parameters to some kind of model output or an error in model output. And the reason you do this is because the perturbed parameter ensembles that I just described are expensive, and because they're expensive, you can't run thousands and thousands of members. But the surrogates are fast statistical models, and you can literally run thousands of simulations with them and more densely sample your parameter space. They can then be used to do this kind of calibration exercise, and there's a lot of approaches to doing the calibration exercise, but basically what you're doing is doing some kind of optimization problem where you find the best parameters to match your observational constraint or whatever constraints you want to put on your model output. And in most cases, these emulators are differentiable, which the machine learning people tell me is useful. The surrogate-based calibration is basically another iteration loop, so similar to the slow iteration loop that we do now, but it changes things. So now we're gonna, and this is two different versions of what I think is essentially the same thing, and it's described in many papers. So this Watson-Paris et al. Paper does a kind of a high-level conceptual view. I recommend it. The Cleary et al. Paper, very rigorous for the brave. Or the mathematically inclined. So what we do, I've already described it. You run your model, you have your physical model, you run it a bunch of times with different parameter combinations. The way we do it is with Latin hypercube sampling. So every parameter that we identify as being part of the parameter ensemble has a range, and then we assume a uniform distribution within that range, and we perturb all the parameters simultaneously to try to equally uniformly sample the parameter space. So remember, that's going to be like a 45-dimensional space. That produces a sparsely sampled perturbed parameter ensemble. We use that along with observations to give you an estimate of the error in the model, to train an emulator, this fast statistical model or surrogate model. And you can use any kind of technique you want to do. It's basically a regression problem. Once you have that statistical model, you run it many times to densely sample your parameter space. And then you do this kind of inference calibration step where you find the parameter combinations that are closest to your observational constraints. And then you go back to your physical model with those parameters to test, to validate the parameter choices. That's basically repeated here. You can do this in many ways. So there's neural network versions of learning the parameter space, or there's Gaussian process emulators. There's different methods to do the matching, history matching, or ensemble common sampling and things like that. All these things don't really matter for the general process, which I just described. Basically what you're doing is you have your parameter space, in this case, a two-dimensional parameter space, so you just have two parameters, and on the vertical axis is some measure of skill. You have your dots showing your perturbed parameter ensemble, and you're trying to basically find the functional form that fits those dots the best. So, like I said, a regression problem, and you can do that however you want, and you basically want to find that peak, the red peak in your parameter space, and sample that part and rerun your physical model with those parameters which maximize your skill. This is an example of doing this with CLM. This is from Linea. Looking at gross primary productivity on the vertical and leaf area index on the horizontal. The lines show the observational constraints. The blue dots here show their perturbed parameter ensemble, so running the model, the CLM, a bunch of times, 1,500 times, and you get this big spread of solutions. You take that as a training data set and train an emulator and then resample your parameter space. So you have this much denser sampling, and then you apply your constraints. And you can do this in many ways, like I said, but you apply the constraints and basically do a selection of parameters, and then you'll go back and rerun CLM to see if it works. And they do this for a couple of different in a couple of different ways. One is constraining leaf area index, I think, and the other was constraining 3 things at the same time in the green and the blue, dark blue dots. And you can see that the ensemble spread, now rerunning CLM with the calibrated parameters, reduces your error, the error in the spread of your ensemble, and gives you a better solution with respect to observations. You can make sure, you can go back and compare the emulator version with the actual CLM version to make sure that they are giving you similar answers. That's shown on the top, so you get these regressions that almost always look pretty good, like once you've gotten to the point of writing the paper about it. So they're pretty boring to look at because they're lines. But you can also validate the model by looking at the default model, so the hand-tuned model, for example, and the calibrated model on the bottom, and the mean absolute error in this case for leaf area bias goes down quite a bit by choosing these calibrated parameters. I wanted to point out an example from Greg Elsasser using the GIS model E3 atmosphere model from the GIS, the center formerly known as GIS, maybe. And what they're doing, and can you see this? Yeah, okay. So there's a couple of reasons to do this. So they're doing basically the same process, building an emulator, applying a number, like 30 different observational constraints to find calibrated physics parameters, and then rerunning the physical model as a calibrated physics model. The red dots in these plots are their default hand-tuned model, and the black dots are their PPE, and the colored dots are their constrained PPE. So after the process. And one of the things that they were trying to do is look at this total cloud cover associated with shallow cumulus convection. And in their hand-tuned model, they were very far away from the observational constraint, which is this green line. But so this is what I was talking about with that kind of ambiguous tuning. When you do a hand tuning, you find one path into a soft spot in the parameter space. But when they do the calibrated ensemble, the calibration finds all this parameter space that they weren't exploring with their hand tuning, and they can actually get, oh, I lost it. They can actually get a number of calibrated parameter ensemble members that are much closer and actually sometimes like right on the observational estimate. And remember that they're actually, at this point, they're constraining a whole bunch of things. So they're trying to match radiative equilibrium as well as a bunch of other observational targets simultaneously, and so they're doing better in terms of this parameter, or this metric, as well as all their others. But you can also get into a different situation, and that's shown down here. This is the stratiform cloud fraction, so another version of cloud fraction, and their hand-tuned model is, I can't see this, is that red dot down there. And you can see that the colored dots, their calibrated physics ensemble, are all really close to their hand-tuned model, which is often the case when you do these tuning exercises. Often the hand tuning is very close to the machine learning version of the tuning. But in this case, all of the dots are very far away from the observational target. This is indicating that there's probably structural error in the model. The equations that they're using to get stratiform cloud fraction are incorrect in some way. And so you're never going to tune and get a good simulation in all your other observational constraints and this one. So you have to go back to the drawing board for that. And this is one way to identify these kinds of structural errors. So these are a bunch of pros of doing this kind of machine learning approach to automated calibration of the model, but that comes with a lot of challenges still, and a lot of them overlap with the dilemmas that Cecile was talking about. So the methods, in terms of methods, there's still a very large number of parameters to explore. And actually, a lot of the parameters that we're looking at in these kind of physics ensembles so far don't ever talk about, they never even think about doing the many parameters that are in the dynamical cores, for example. And there are lots and lots of parameters across the ensembles that we don't perturb in these kinds of experiments, and we should think about whether that's important or not. The sampling strategies to generate your PPE are not great, and they could be better, and there's a number of ways to do that, but nobody knows the best way. Emulation architecture, whether it's neural networks or Gaussian processes or random forests or whatever you want to do, there's lots of choices and nobody knows if there's a best way or an optimal way to do it. And there's lots of ways to do that along the way, including what are your penalty functions, which means choosing your observational targets, which ones are the important ones. In terms of computation, you still do have to run the forward model a lot of times to generate your PPE, so you're not getting away with a completely cheap way of tuning your model. It's still computationally expensive. It's just distributed in a different way in time. And we don't know, for example, the length of the simulations that you need to do a good job of this kind of automated tuning, or whether the forcing matters, if you should do this in a pre-industrial climate or a transient present-day climate. Those are basically unexplored ideas. And then there's a bunch of cultural issues that you have to deal with. This is a big change from what we've been doing for 20 years, and it takes a lot of effort to like build up that confidence in this kind of new method. And we've tried it with CAM6, and we're not quite there yet culturally, but we're going to continue to try to build up that confidence. The problem is you want to be doing both versions at the same time, and that's basically impossible with the resources available. You also have to there's a psychological adjustment, because what you do here is you take your physical model, you're going to end up with a whole bunch of parts of parameter space that are equally plausible. And so instead of like one at a time testing them, you end up with a whole bunch of sets of parameters that you should then make a constrained parameter and evaluate them all at the same time in a new parameter ensemble. And that means that we're also going to have to change how we probably do the diagnostics and the evaluation of that constrained physics ensemble. And then the beast is coupling, which I think opens up all of these issues and multiplies them and makes them hard again. So that's it. Thanks.
Thanks so much. Yeah, let's ask for questions, and they could, be questions. There could be questions for both, of course, Cecile and also Brian.
Yeah, and does it work? Okay. Yeah, sorry. I just want to add something to what Brian said. First, you may wonder why we have been doing untuning for such a long time, but there were several efforts in the past to try to automatize the tuning, and until now they were always like they were worse, not performing as well as a bunch of scientists sitting in a room. And also the last thing that I want to say, that Brian was telling that we still need, if you go on your last slide, then they were just, you have a lot of slides here. Yeah, then Brian was talking about that we still need to run the physical model for training, and right now we are getting help from the machine learning group to try to solve the Labrador Sea problem. It's just a test to try to see if it works, but they are going to look at the salinity and to look at the depths of the mixed layer in the ocean around the Labrador Sea. But then they were asking I asked them how many simulation do you need, and they say, oh, maybe 50,000, and I say, I can give you 15. It's just then this is really like to train the model, they need to have observation. Then I wanted to mention this because I think it, yeah, sorry for.
So I wanted to link a question from yesterday in David Lawrence's talk to actually both of what you're talking about and Brian's last point about coupling. So the question for David Lawrence was, is there a possibility that sometime in the future we'll see, instead of a data atmospheric model or a dynamical atmospheric model for CAM, a machine learning atmospheric model? And I think there's steps in that direction, but I'm wondering if there's been discussion that might be a way to solve this. So like Brian, the way that you're talking about emulators is slightly different from the machine learning, like we're mimicking CAM's stepping process. I mean, what if you had a version of CAM that mimics CAM, but also has layers on it that take in the parameters from the PPE and modify the output so it looks like a PPE. You couple that in the couple model and see you drive which states drive you into these cold states hundreds of years in the future, but maybe without quite the computational cost of the full coupled model.
Yeah, and I think there are steps being taken toward that. So we have this thing called the CAMulator now, which is an emulator, a real emulator of CAM, the system, which I believe they're trying to like move toward coupling that, which will be the first big step toward that. And then I don't think that they train with the parameter values. I think they just take the default parameter values. So that would be another iteration on the CAMulator would be to also be able to learn the parameter sensitivity along with the physical system sensitivity. Cool.
Yeah. You showed the Labrador Sea and the intermediate depths of the Southern Ocean as where you trace back some of these problems. Are those like the ones that you find most useful? Are there other areas of the atmosphere or ocean that these kind of coupling problems show up?
Yeah, for the Labrador Sea, it's because we want to have a Labrador Sea free ice-free, it's the reverse order in French. We want to have the Labrador Sea that's ice-free, but we have for example, the ITCZ has been a problem forever. Then there is other bias in the model. Yeah, I just show a few examples of things that is from the problem, but it's not the only thing that we are looking at.
I was wondering if we look at the model initialized with observations such as SMILE project, then do we see some consistent model bias drifting away from observation as tuning process?
Yeah, then in the past we were doing a lot of, we were doing forecasts and we were both very involved in this effort, and you even later than me, we were doing forecast, then we will initialize the model and we will see how it drift. There are other efforts till now when they are doing, what Pat is doing. Pat, nudging, there are some nudging effort, but it's not, I'm not really involved into this.
But we do have a number of more predictability focused efforts, so they do initialized prediction. They're more interested in predictability, so they do a lot of like bias correction and things instead of looking at the drift like Cecile was just describing. What we've seen is that it drifts very quickly in general, like it drifts at least in the atmosphere only simulations where you don't worry about coupling. They're short, basically weather forecasts. They drift toward the model climatology very quickly.
Colin first.
Yeah, this goes a little bit along, I think nudging was just mentioned. I was curious, are there any efforts, so for numerical weather prediction, a lot of times they'll do data assimilation and look at the increments to see like how the models are responding. If you're constantly dragging the model to a particular state, it may give you an indication of bias in the model. Is there any work ongoing right now, either with nudging or with data assimilation in CESM for the purposes of tuning?
It comes up. Julio's here. Yeah. Julio brings this up. I think we want to do it.
Yeah, we always say we want to. Yeah, we always say we're going to do it. I was just about to send Will Chapman an email.
So we should hire an enterprising young mind from the summer school. That's what I'm hearing.
I think that money's going to be raining from the sky pretty soon, right? So.
When you say biased, is that model minus reanalysis, that difference, or are you using like raw observational data to define bias?
It depends. Sometimes it's reanalysis, and sometimes we are comparing to observation. Depends on which variable. Often we use the word observation for reanalysis, but
Thanks.
But we use both.
Mm-hmm. Question for you, Brian. On your point about the culture, what would you do if you developed two completely divergent but equally plausible or skillful parameter sets? Is there some physical basis to decide between those, or how do you settle that?
Yeah, you have to do, I think that's plausible actually. I think we will find that, and what we'll have to do is then have like out of sample tests, right, with different observations or different physical process, or you couple it and see what happens to INSO or something that you're not tuning for explicitly to make that subjective call between them. Yeah, I definitely think that's going to come up.
Thanks.
You mentioned that in Cam 6 there was a
fix to the laboratory C problem, but then are you still implementing that model in CAM7 and then still seeing the Labrador freeze problem?
Yeah, it was not, we didn't implement this estuary box model to fix the Labrador Sea. It was that they were doing research at the time to use this, and they are still using this model, I believe, in the ocean. Right now we are focusing on the runoff that's going into the Labrador Sea and then bring fresh water in the model. Then we are really looking into this. This one was not a fix for the Labrador Sea, it helped us. It was something that we were implementing that was helping us. And right now we are even considering there were a lot of improvement in the ocean model, and we are thinking to step back some of the latest development, because right now we have a version that's more, the ocean model now is MOM, and there is like more the out-of-the-box version that we're using right now doesn't give the Labrador Sea freeze, at least not yet. Because the problem is, I was showing, sometimes it takes a very long time, and suddenly it freezes, and when it freezes, we never saw it defreezing so far. Even that there were some people that said that, I think it was people from Norway that are using a version of CESM, and they were their own version of CESM, and they had seen the Labrador Sea defreeze, but we never saw this.
Short question, do any other models, like internationally, see a Labrador freezing problem? Or is that
Yes, then it has been, do you have this in CESM or? I think there are other model, I don't know which one, but it's not, we are not the only one, but a lot of modeling centers say, okay, this is frozen, but here we want to have it ice-free.
I was wondering, Brian, if you could talk a bit more about the how tricky the cost sort of component is, especially sort of how you decide if a parameter's a good parameterization in the machine learning sense, where you can be predicting to out of sample data anyway.
Do you mean how do you define your cost function?
Yeah, and then how do you know that solving that cost function is like what's going to give you a good prediction in 200 years, say?
Yeah, I think that there's a lot of ambiguity about how to do it. So you have to, I think what it boils down to is that we're going to have to try many different kind of cost functions in the training and maybe generate ensembles of surrogate models, which is what the LSAT paper does actually. They use a neural network, but they generate, I think, 6 different neural networks and take the average of them to be their surrogate model. And I think that you could do the same thing with different cost functions instead of different network architectures to try to mitigate overfitting and also try to understand, or well, maybe not understand, but just get around the idea that you don't have a perfect metric for what is right and wrong. Yeah, I don't know. Yeah.
Just a quick question on the parameters that you select to send to the emulators. You said there were 3. Are those the 3 that you're interested in? Or are those picked from the parameter space using some kind of like genetic algorithm or something similar to that?
I think for the CLM example, they did something to select a few parameters that they deemed important somehow. I don't know the details of how they did it. I think in general, what we've been doing is going ahead and trying to take as many parameters as we can, fit the surrogate model to that, and then try to calibrate based on the more densely sampled full parameter space down to get smaller parameter sets for all the parameters.
Okay.
Instead, if you know a few parameters are important, then you can do what you described, like just pick those and do it. But you often don't know which parameters are important. And what we're finding with exploring CAM6 perturbed parameter ensembles is that sometimes parameters become parameters that you would think are unimportant in the full PPE as you hone in on parts of parameter space where you're getting better skill, additional parameters start to become more important for how you move around within that bit of parameter space.
So just to recover a bit from stumbling over the nudging question, what are people thinking about machine learning with short forecasts? I mean, part of the problem with tuning a climate model is that climate doesn't emerge for a long time. But I think we've had the experience that short-term runs don't really give you useful information for climate tuning. Or do they?
I think they do. I think they do. I don't know. Travis might have other opinions about this. I'm of the mind that I think that we can do a good job. I suspect that we can do a pretty good job of getting tuning parameters or sets of tuning parameters from short runs, trying to avoid the feedbacks that emerge when things start to interact with each other over longer timescales. So this is an active project that I'm trying to spin up right now, is doing initialized PPEs to explore exactly that idea.
For how long?
10 days.
Okay.
Can you maybe give us a little bit of an indication, how many tuning parameters are we facing actually? And maybe it's specific to the atmosphere, since you deal with that the most. Are we talking about 10, 20, 100?
We are talking about 10. We have a lot of tuning parameters, but the one that we are playing really actively, it's not hundreds of parameters.
Yeah, okay. And that comes out of your own experience with the model?
Yeah.
Yeah, and the PPEs tend to support that those parameters are the ones that have the highest sensitivity on their own. But when you start to explore the multi-dimensional space, we're working with 40 to 50 right now in the atmosphere. But that, like I mentioned, doesn't include any parameters from the dynamical core, doesn't include really gravity wave drag, doesn't include a lot of surface interaction things. So it's really just some of the cloud, club, aerosol, and convection.
And usually, because when we start to explore new tuning parameter, we are going to want, for example, to look within at a bias in a particular region, and then we know that parameterization will matter at that region, and then we start to explore some new tuning parameter in this region. But by hand, it's like not using a lot of tunings.
Maybe last question. Okay, maybe you then, and then we at the session, yeah.
If we accept the idea then that sort of machine learning for tuning parameters is sort of like a very good way to go, what's like the barrier to just doing it for all of them? Like why wouldn't we?
Identifying them. Some of them are hard-coded in the model, they're hidden from us. And then there's it's not hard to do, but it requires effort to just literally turn those hard-coded parameters into nameless parameters that we can easily perturb in an automated way. It's finding them and doing that.
I could imagine that it could make sense, but I don't think that's an explored area to even have different tunings for different regions. But that's probably not what we are doing. Yeah, we are doing constant tuning parameters for all regions. Yeah?
Currently, that's what we do.
Okay. All right, then thank our speakers one more time. Okay, and the final block is about the prospects, where we are heading in the GCM and the machine learning community. We are starting off with Colin Zarzicki from Penn State University, who's of course also our mentor for the MPLS group. And then we finish with prospects. So he talks about the GCM prospects for system modeling. And then we finish with Travis O'Brien from Indiana University, and he talks about the prospects for the machine learning world.
All right. I like how the last time I was in the seminar room, I got yelled at for getting too close to the screen, and now there's like a wall here. I don't know if it's just for me, but I definitely got my hand slapped. So, I kind of want to talk a little bit about, really I'm going to actually focus on some of the kilometer scale modeling efforts that some folks, I know Mark kind of touched on a little bit. and where I think some of the challenges are. So, I mean, I could certainly fill up the time talking about stuff that I'm interested in or stuff my group's doing. But I really want to kind of leave all of you with like an idea as to where I think some of the big gaps, the big challenges we're going to face are. So with that acknowledgement, a lot of this material I did present last year at a workshop that was really focused on Earth system prediction across timescales and some of the grand challenges for the next decade. And then over there, that's a simulation actually of Typhoon Mawar using the screen model that Mark talked about either yesterday or 2 days ago. So I always like to show this slide to just kind of motivate it. It's probably at this point, Friday, you guys have figured it out, but this is kind of the impact of grid spacing on simulating particular discrete features in the atmosphere. So this is if we had 4-degree boxes. I have a particular weather feature or historical feature that's represented up here. You might get a couple people that would guess what this is, but it's really tough to see. These just look like a lot of boxes. We could move down the resolution spectrum. So this kind of gets us to 1 degree, which is sort of like what our CMIP class models are these days. And you're starting to kind of pick out what's going on from like a synoptic scale perspective, maybe not seeing a lot of the fine scale structure. Now maybe more people kind of see what's going on. But as we move to these finer spatial scales, which are traditionally kind of in the purview of numerical weather prediction, we see a lot more of that kind of mesoscale spatial structure come out. This is a simulated satellite image of a Hurricane Sandy forecast we ran, actually probably like 5 or 6 years ago at this point. I should probably update my figures. But I think this kind of really highlights sort of like what we are trying to look at with some of these high resolution simulations. And there's been a lot of papers talking about this, many authors in the room. Grid spacing, as you decrease, you get a better representation of a lot of processes in the climate system. And a lot of the questions circle around, what are important for our simulations? And what are we interested in? Like, what is the end game of your, your project? And that kind of goes into the design considerations of which resolution is one of. I'm particularly very interested in extreme weather. I'm a meteorologist by training. Right now, I'm in a meteorology department, so I have a lot of students who are like very interested in weather events. But I personally think this is a key thing for us in the climate community to be thinking about. It's very societally important. So this is a really nice data set that unfortunately has just been recently killed off. The NOAA $1 billion disaster data set. But you kind of see this is starting to really get that linkage between kind of societal impacts and what's going on with the climate system. So if we think that there are modulators, drivers, changes going on in this extreme weather, this is how the general population really feels kind of the climate system impact that most of us are interested in. So why is resolution important for this? I just have a couple motivation slides, but this was actually some work way done. This was during my PhD, so I was probably a DCMIP student when I was doing these simulations. But in the top, we have tropical cyclones looking at hurricanes that were in a uniform CMIP class 1 degree run. In the middle, that's a variable resolution run, which we've talked a little bit about these regionally refined grids this week, but we put a high resolution nest over the North Atlantic that gets us down to 25-kilometer grid spacing. This is also with the SE or home DICOR, so we're using that. And then the bottom, that's the observations. That's from a data set called IBTrax. But what I mostly just want to point out is that if you look over the North Atlantic and the 1 degree and the variable resolution runs, you see that the North Atlantic looks a lot more like observations when we turn up the resolution wick to 25 kilometers. And what was really cool is if you actually zoom in on this and then you actually plot where those hurricanes formed as a function of the maximum intensity they reached, we also see some kind of process level improvements from the resolution. So in observations, most of our really big like Category 4, Category 5 hurricanes in the North Atlantic originate in this stretch between Africa and the Caribbean, known as the Main Development Region, or MDR. And the model actually picks up on that when you turn up the resolution. So this is also some confidence that we're getting the right answer, but we're also starting to get it for the right reasons. And then last, I just pointed out here that you also start to get this modulation of storm frequency with climate signals. So one of the things we're really interested in is climate variability with these kind of long-running simulations. But obviously, if you're interested in looking at high resolution, you want to make sure that you're getting this physically consistent representation. So for example, in the North Atlantic, historically La Nina years are more active than El Nino years. I'm not going to get into the details of why, but the model is able to pick on that relationship as well. So this is just a quick movie. Again, this is also a couple of years old now, showing you what a high-resolution climate model looks like. And I would actually say this is kind of the state of the art now. So there's this model intercomparison project. I think Isla mentioned it this morning, high-res MIP. But we do have a lot of centers around the world that are running kind of this quarter-degree class type of simulation. And this data is now, when I was a graduate student, it was kind of, you had to know who to talk to and you had to find the data on someone's system. Now we have a lot of this 25-kilometer data on things like ESGF. Now, we're not running full deck type experiments with it, but I think it has become fairly mature in its application. What I do want to talk a little bit about is kind of what's next as we go in the kind of the model resolution hierarchy. And this is, I would argue, probably the next frontier that a lot of people are starting to look at, which is this idea of K-scale or kilometer scale models. So I'm just going to show a couple quick examples here. This is one example. So Bjorn Stevens has been leading this project known as DIAMOND, which stands for Dynamics of the Atmosphere General Circulation Modeled on Non-Hydrostatic Domains. So a lot of ChatGPT fudging in that acronym there. This was before ChatGPT, so just a lot of thought, I guess. But the idea here, and Mark showed a couple figures from Scream doing this, but it's that you're actually getting to the point where digitally these models are essentially twins or surrogates of the Earth system. And I really like this figure because I honestly can't remember. One of these is a satellite image and the other of these are all simulated outgoing long-wave radiation maps from different Earth system models that are run at kilometer scale. And so the idea here is that, we talked about it, we're not parameterizing convection. I wouldn't really call it cloud resolving. We're in this cloud permitting space. But essentially, we're trying to do a much better job reduce some of the biases associated with a lot of the parameterizations here. So I just want to show kind of one example of what my lab's been working on and where I think some of the benefits are, the value added from these type of simulations. So one thing we've been doing is working with CAM MPAS. So some of you have also been working with the MPAS Dynamical Core during this workshop. We've been running these simulations where we have a mesh that we can move around the eastern United States. So we've been working with a group of stakeholders in Florida. We put a 3-kilometer nest over Florida. We're actually using the CAM5 physics, which I actually really like. It's a kind of a nice balance of fast for high resolution simulations, but also skillful. And we're essentially running these initialized runs that we just talked about a couple minutes ago. And I really like this. I refer to this as a Turing test. I did steal this from this idea from the Diamond group. But essentially, I put up these 6 hurricanes, and I can tell you, okay, one of these is a modeled hurricane. Can you find which one is the modeled hurricane? And if I asked you guys all to raise your hand, I would hope that most of you would say that top middle panel. It looks blocky. There's grid. I can see that. But really, it was a bit of a trick because I actually put up 2 modeled hurricanes and 4 observed hurricanes. And my guess is none of you had your eyes drawn to the one in the bottom left, which is actually also a simulated hurricane, the other 4 being observations taken from satellite images. But again, just based on the subjective eye test, we're getting to this point where I would argue it's becoming almost indistinguishable, depending on what you're looking at, the models from the real world. And then just a really quick slide on where I think at least one component of the value added is. So we've actually worked with a group of stakeholders in Florida. The top row, those are, we've reforecasted 4 important hurricanes, Ian, Irma, Isaac, and Faye. Top row is 28 kilometers. The middle row is those 3-kilometer CAM MPAS. These are using exactly the same physics. The only thing we're doing is turning up the resolution and turning off deep convection. I think we changed time steps for radiation, a couple other things. Bottom is radar gauge data. And then what we've actually done is done some statistical comparisons on them. So somewhat interestingly, if you look at the storm total precipitation, these 28-kilometer models actually do a reasonably good job, which is actually somewhat comforting. Again, going back to getting the right answers for the right reasons. But where we see pretty much across the board, I haven't been able to find a configuration where the 28-kilometer model beats the 3-kilometer model for hourly precipitation. So getting that precipitation rate, those extreme values kicked out. On the right side, those little pink boxes are telling me that every time we run a 28 versus 3-kilometer comparison, the 3-kilometer wins in terms of matching that radar data. And this, I think, is pretty important for some stakeholders. They're very interested in looking at, for example, hourly precipitation extrema for things like water management, for sewer operations. And currently, they're using a lot of statistical fits to climate data, but it might be interesting to see how some of these models can be applied. And then the last piece of eye candy we have here, since we have been talking about SCREAM, is we've also been running some of these kilometer scale simulations for synthetic storyline generation. So we've been working with a group at PNNL that actually has a machine learning electrical outage model. And what we've actually done here is, this is a completely made up hurricane. We actually pulled it out of a climate simulation. We downscaled it to 2 kilometer resolution, I think it was 2 kilometer, 1.6. And then we actually passed those wind fields that come out of the model into a machine learning algorithm that predicts what the county level outages are going to be. And we've been working with some utility stakeholders to see, what kind of data here could be used in their operations. I just have a slide on this real quick. We're going to actually talk about computational cost in a few slides. I'm a big proponent of some of these regionally refined or variable resolution frameworks. I think most of you in the room are not going to have the capacity to run global 3 kilometers on any of your local university clusters. The variable resolution 3 kilometer simulations, however, regionally refined, they're still fairly expensive. But if you wanted to run like a year of the 3 kilometer mesh that I showed, it takes about 410,000 CPU hours. And as grad students or postdocs, most of you can actually get, I think, like $500,000 for free from Duratio, just having your advisor send a letter. So I do think these are becoming practical also for research, not just something that needs to be done at a national lab. Okay, so now I want to pivot from some of the exciting stuff that's being done in the field down to looking at kind of like what are still the challenges and where are some of the gaps that we're at. So, one thing I always like to say is, okay, well, great, we're at 3 kilometers, we don't parameterize convection, problem solved, mission accomplished, put up the big banner, let's all go have beer. There was a paper by scientists down in M-Cube, down at Foothills, Chris Davis, in 2018. We used to have a lot of lunch, I wouldn't say arguments, conversations over the ability of 28 kilometer models to simulate tropical cyclones. And he wrote a paper that said, okay, if you can get to like 14 kilometer grid spacing, you do a pretty good job of representing the axisymmetric structure of tropical cyclones. So diamond runs, these are all 3 kilometers. So we said, okay, all the cyclones are going to look the same in the diamond runs. So the middle panel, that's by a colleague or another scientist down in M-Cube, Falco Jute, he went and looked at hurricanes in diamond and found that there's like a massive discrepancy, even a larger discrepancy at 3 kilometers than there is at 28 kilometers. So obviously just turning up the wick to 3 kilometers, turning off convection does not solve this problem of trying to figure out what's going on and how these models, they're not converging. If anything, they're diverging in how they're representing some of these structures. I personally think most of this has to do with boundary layer and turbulence parameterizations, but also could probably be due to things like physics dynamics coupling that we've talked about, could be due to radiation, things like that. So just some of the ways that we've started exploring this. So one of my former PhD students, who's actually now here as an ASP, did some simulations looking at CAM in 25 kilometer models. He compared against large eddy simulations. So I don't want to spend too much time focusing on this slide, but essentially the blue curve in B, that is the effective diffusivity of a tropical cyclone simulated in CAM6, and the orange curve is from a large eddy simulation, which is supposed to be representing the truth. And we find that that's not great. The CAM model is kind of estimating diffusivity that's much higher than the large eddy simulation. And one of the things that we notice is this leads to a very large bias in the height of maximum wind of tropical cyclones simulated at 25 kilometers. So yeah, that's bad. So these are things that as we were talking about tuning and on the road to from CAM6 to CAM7, we've been looking at. So Isla earlier talked about idealized models. So one of the things that we set up that I actually probably still need to get in the CAM trunk at some point is we have this F-plane tropical cyclone case where you can stick the tropical cyclone in the model and it just sits and it spins and it spins and it spins for weeks at a time. But what you can do is you can kind of try to isolate some of the physical processes without the complications of land and all sorts of other synoptic meteorology. And so we've been really focused on the boundary layer parameterization to look at this. So one of the things that Kyle did was he did these parameter sweeps, not unlike sort of some of the stuff that Brian and Cecile were talking about. And we found a couple parameters, for example, in Club that really govern the eddy dissipation. And as you increase the eddy dissipation in the boundary layer, it leads to reduced size eddies and less diffusivity. And you can do things like bring down the height of the maximum wind, which is a key bias in the model. And yeah, so I have a lot of pop-ups on this. But at the end of the day, I think one of the big open areas, and I think I've seen a lot of the community moving towards with these high resolution and next generation diagnostics, is this idea of process-oriented diagnostics. So not just looking at, in a weather sense, this might be the 500 millibar skill score, or looking at like really basic climatological means, but what are the processes in the models actually look like, and how are the different parameterizations engaging with them? If you get a good climate, but then all of the kind of synoptic or subsynoptic scale features within the climate are poorly represented, that becomes a bit of a challenge. So another example of that is kind of comes out of the Earthworks project. So Dave Randall, I know, was here earlier this week and probably showed a couple results from Earthworks. This is a kilometer scale version of MPAS and CAM. And one interesting thing they found was that when we, so on the left, this is a squall line. That's observations of the squall line. The second panel, that's using MPAS with WRF physics. So like for those of you who are familiar with weather models. Then we just took the CAM6 physics and tried running. That's the third panel. And suddenly it looks nothing like observations. And after a lot of trial and error, they actually found that there was one single parameter in the microphysics scheme. Really what it's actually doing is toggling the cloud fraction that the microphysics sees to either 0 or 1. So it's kind of related to what Rich talked about with the cloud overlap earlier. And then suddenly just turning that one switch on gives us the right panel. So that squall line looked much, much better just with flagging this one switch. The bottom shows that the folks down at MCubed have looked at a little of these kind of the cold pool evolutions associated with the squall lines and things like that. But I think this is a key point showing that you can have parameterizations that that behave very well at 25 kilometers. You turn up the resolution to 3 kilometers, and suddenly from a physical interpretation standpoint or a physical fidelity standpoint, you begin to get some kind of interesting results. I don't want to say questionable or anything like that, but we have to kind of think about that. That leads into this obvious this point, which has actually come up a few times, which I think is actually probably one of the largest gaps or uncertainties that we really have to challenge or go after these days, which is a scale-aware physics. So there's this huge push either for regionally refined models or for modeling centers to move towards unified modeling systems, so things that can run well for weather and climate. I always like to say, if your climate model can't represent weather, that's not a great thing. And if your weather model can't represent climate, that's also not a great thing. So we want to make sure that, or we want to try to develop models that work well across scales. But for example, you may have a regionally refined model where the scales that you're representing in the fine domain are very different than the scales you're representing in the coarse domain. And what are the processes at play? What needs to be parameterized and what doesn't? This paper is, it's an older paper. It's actually 12 years old now from Sarah Rauscher when she was working at, I think, Los Alamos. But I really like this paper. What she did is she ran a variable resolution aquaplanet simulation. And in an aquaplanet simulation, everything should be zonally homogeneous. And she got this large gill response in the middle, in the 200 millibar eddy velocity potential. The bottom is what you get with a held Suarez simulation. So we actually knew it wasn't the dicore that was driving the sensitivity. It was something in the moist physics. And if you look closely in the top panel, as the resolution increased in that little dashed circle, the precipitation responded to have a stronger precipitation response in that area of high resolution. You got more latent heat release. You got this kind of like big circulation that developed. So the only thing here we did was just turn up the resolution and we got some sort of asymmetry which shouldn't have been there in the simulation. So this is kind of highly indicative of not having, for example, or places where having scale-aware physics might be more helpful for us. You guys have really been focused on this with the dicores. I think the dicores are still a thing. We've looked at this in previous DCMIPs. You guys are looking at this in particular. The squall line case, I think, fits in well. But many models, when we looked at the last DCMIP, we figured, okay, we're running these supercell test cases. We go down to 250 meters. Everyone's going to kind of converge to the same answer. And that's really not the case. So you have a lot of this kind of diversity in how things like diffusion are handled, how the coupling is handled. And it's certainly not a solved problem, even when you're pushing down to the sub-kilometer grid spacing. Another challenge we have is model initialization. So we've talked a little bit about how these models are now being used for kind of more, I don't want to say forecasting, but looking at things in initialized sense where you have an initial value problem. You put some sort of initial conditions in and see how things evolve. So the panel on the right there, that was a paper let's see if I can get the cursor going, a few years ago out of one of the DOE groups, and they were trying to reforecast the derecho of 2012, the big one that went through Washington, D.C. So this is what the right answer is if you look at, I think it was NCEP-IR data, so satellite data. And they were really trying, what they were doing is pulling in reanalysis data. They couldn't get anything to work either with ERA 5 or ERA Interim. And it was only when we actually brought in data from the US High Resolution Rapid Refresh that we were able to capture the correct answer. So this really showed that it wasn't the model's problem here. It really was something to do with the initialization. And as you go to these scales, I think we need to start thinking about how we're doing the initialization more often. Historically, in the climate community, it's mostly just been kind of like cram and go, but things like data assimilation or nudging may be relevant. This is just a brief advertisement, but one of the things I've been very interested is initialization of all of these tools. So we have our group maintains a software package called BetaCast that allows you to initialize models that use SEAM as their wrapper, so DOE models as well as CESM, which you guys have been using. So it can go and pull data from various different sources and get the model spun up and ready to go. But I have a wish list here, and what this wish list really represents are gaps. So for example, we need more user-friendly data sets to leverage, but we also want a lot of robust error checking for model configurations. You want to be very careful that when you initialize these models, you don't just get an answer and then either say this is the greatest thing since sliced bread, or blame the model and say, this model, like we saw on the last slide, this model's terrible. It could certainly be more of an initialization problem than a model problem. Computational challenges, I'm just going to breeze through this because this has come up multiple times, but you guys hopefully know by now that if you go from like a 100-kilometer model to a 3-kilometer model, I have some numbers on here, but essentially the amount of memory that you need to run one of these simulations is an order of magnitude larger. So if you're talking gigabytes to terabytes of memory, now we're talking terabytes to petabytes. And then the wall clock time, you actually get the added penalty of the CFL constraint. So just running 1 unit, if that's like 1 year of a 3-kilometer model, that is 32,768, assuming linear scaling, times the capacity you need for a 100-kilometer model. Or to flip that on its head, if you run 1 year of 3-kilometer simulations, you could run a 32,000 member ensemble of 100-kilometer simulations. So again, they're kind of got to think about those scientific questions that we need to ask. So as we kind of get toward the end of the presentation here, I want to hit on a couple things that are sort of near and dear to my heart, which is also, we haven't talked a lot about this at DCMIP, but as you move to these higher resolutions, you put a lot more pressure on things like the data storage and analytics. Interestingly, you guys have seen a lot of this when we've been using Azumi, mostly just because of the file system, but also just if you can imagine, this becomes a bit of a size problem. So, when I was a grad student, I tracked tropical cyclones. I could write a tropical cyclone tracker in serial and let it run for like 4 or 5 days and whatever, it would find all my cyclones. But certainly, I don't think I could do that nowadays with any of the new class of data sets coming out. So there's a big focus on parallelization, optimization, operations on arbitrary and unstructured grids. And I do think the second bullet point here is going to be very important moving forward, which is this idea of compression. We can't just save full double precision, everything we want all the time. So I think we need to be doing a better job of exploring lossless compression as well as lossy compression in some cases. So there's a good paper, actually a couple papers I think by Allison Baker, looking at lossy compression of various things and essentially asking climate modelers, can you spot what is the data set that I compressed in a lossy sense? And for many variables, the answer is they couldn't tell the difference. But for some variables, they could. So, you kind of have to be selective on how that's done. So this is just another motivation slide talking about data storage and analytics. So some tools like Tempest Extremes, for example, which is a Lagrangian feature tracker some of you are familiar with. We've really tried hard to make that operate on unstructured grids. Actually, I think that's from Travis was involved in some of the ClimateNet stuff over there. Maybe he'll talk a little bit about that. That's some machine learning kind of image detection. But how do we data mine these data sets? I mean, we're producing, some of these models will produce petabytes of data, but at the end of the day, if you just want hurricanes, you just want atmospheric rivers, that's kind of what you're looking at. So yeah, there's some more of a wish list there. Many of you have already started playing with this. I also wanted to just draw your attention to this idea of UX-Array, which is an unstructured data visualization tool that's actually primarily developed here at NCAR. But when you get to these kilometer scale models, you can't just be carrying around duplicates of 3 kilometer data sets on regular lat long grids. It's just not, it's not efficient, it's redundant data. You want to be doing as much of the analysis on the unstructured mesh as possible. So these figures were both created both on the unstructured mesh. There's the QR code for that. And then this is my last slide. But I think these are some of the real grand challenges. So these are all the modeling challenges I tried to touch on there. There are a couple others I had to move to the backup slides. But I think these are some real big open questions. And I think these open questions and what particularly you're interested in really guide kind of how you address those challenges. So, one big thing I think we need to figure out how we're going to handle is, how we're going to resolve that computational tension. We would love to be running high resolution for all of these things, makes great movies, but we trade off the statistical behavior. And, there are some solutions, are there surrogate models, are there emulators, can you do regional refinement? I don't have the right answer, but I think they're all things that people have to think about. So, I have a couple of minutes left. Actually, did a pretty good job. We'll leave it like that.
Since we will be switching to a new presentation in a minute, I do think we should take a few minutes to ask questions now in case Colin wants to get back to his slide deck. Let me ask some questions now, and then we switch over to
Can't be too mesmerized by all those videos.
Okay, Peter, that's up.
So that plot at 3 kilometers showing tropical cyclones where they all look different. What do you think it would look like if everybody ran the same physics?
That's a good question. I think there would be a lot more convergence, diamond runs. I think most of this is, there's a huge diversity in how the boundary layer turbulence is specified here, but it would be kind of an interesting case because we've actually run in these 25 kilometer tropical cyclone cases from previous DCMIP. There's a paper out, and there is still a diversity in that, even when you isolate the physics. So I wouldn't expect the 3 kilometers to get rid of that either. So.
We're interested to see which parameterization or parameterizations are responsible for the diversity.
Yeah. Well, someone could write a proposal and get a, I don't know.
Going back to the compression and data challenges, another aspect that I'm sort of coming around to is that we might need to move away from NetCDF kind of models toward, I'm starting to like ZAR. What do you think about these more cloud optimized storage approaches?
Yes, we've actually been working on getting Tempest Extremes to work with ZAR, and I think there are going to be some benefits to using those approaches. There are some trade-offs in terms of how the analysis is handled, especially when you want a lot of data at once. But I do think that there are definitely benefits of having large data sets in a way that you can kind of pick and choose what you need, especially if you're a student in this room and you don't have access to, 100 terabytes of storage. So yeah, I do think the data side of things is very interesting, and I do think we have to come up with a lot of solutions for these models. Yeah.
I have I think it's a pretty basic question. I'm new to mesoscale weather, but you had a slide where you were showing model simulations of radar reflectivity versus the actual radar reflectivity of a squall line in the Midwest. Okay, it got me thinking, the position of the right along the front there, the position of the most intense radar reflectivity, you can see there's some differences between observed and WRF, but then I was thinking, how do you quantify the fidelity? Obviously you can look at those and see that the other two are no good, but how would I quantify, the fidelity of those two models? Would you recommend?
Yeah, so there's a whole lot of literature on mesoscale verification. It can be as simple as a lot of times what they'll do is they'll put points up along kind of the squall line, look for the timing of the passage, the intensity of the passage. There are also ways to do image comparison of these, basic things like pattern correlation, but you can also kind of shift them. You could do spectral decomposition, which they do sometimes to see how noisy they are. I'm not going to claim to be an expert, but the mesoscale community really loves this verification, especially of these squall lines, supercells, things like that. So there's a decent amount of tool building on that side of things.
Okay, great, thanks.
Yeah. Adam?
I was wondering if you can elaborate on the issues with initializing the derecho over with the 3-kilometer models in Scream. What do you think it was about the rapid refresh product that led to a more skillful prediction?
Yeah, keep going the wrong direction. So her assimilates radar data, and we think that's what it was. So the big thing with the deratio that we found was that no models really did a great job of simulating the convective initiation of the deratio, even operational weather models. So if you back up the forecast before the deratio seed even existed, it becomes very challenging to forecast it. But once the deratio is actually in the fields, then it was there. The problem was it didn't, the ERA 5 initialization, for example, or even the GFS initialization, ECMWF, which we also tried, didn't have the small scale spatial convective structure. But since HER assimilates the stage 4 or whatever it is, the radar data network, the reflectivity, that seemed to be the improvement there.
What's the resolution of the HER?
3 kilometers.
So, I mean, ERA 5 couldn't even support those small scale structures on its 25-kilometer grid, right?
It could not. I mean, the caveat is that HER is initialized from GFS operational, which is order. So if you actually look at the wind fields or the dynamics fields, they look exactly the same for the most part as GFS. But it's that reflectivity that's brought in for the precipitation, the cloud hydrometeors, as well as the vertical velocity field that seem to be the big key in the simulation.
Got it, thanks.
Yeah, let's thank Colin again, and then we transition.
Yeah. Oh, okay.
Yeah, and the final speaker is Travis O'Brien, also, of course, one of our modeling mentors for the machine learning exercises. And yeah, he will present his prospects on the machine learning.
Hello, so yeah, I'm faculty at Indiana University. If you've seen my name in papers before, it's most likely in atmospheric rivers. That's I've done a lot of research on that, on atmospheric rivers over the last 10 years. Some model resolution dependent stuff before that, maybe coastal fog, but it was actually about, gosh, it's probably 8 years ago now, 2017, when Ankur Mahesh was still an undergrad at UC Berkeley, that I started to work on machine learning, actually developing one of the first machine learning, Ankur developed one of the first machine learning atmospheric river detectors that led to ClimateNet that Colin just showed there. So yeah, I've been in and out, I've been adjacent for a while to the machine learning field, and then the last several years increasingly elbow deep in these sorts of models. So this talk is really my perspectives and guesses for where the field is going. But I wanted to start with just reestablishing where we're at. I know that we've had a lot of talks this week, and so I just wanted to bring us back to some of the earlier talks. So we saw in Will's talk, for example, he talked about these 4 sort of categories of how machine learning is used in our field. Totally agree with this categorization. I think just about every paper that we come across in machine learning and atmospheric science and climate can probably be fit into these 4 categories, with a lot of the most rapid changes being in either the hybrid modeling or the model replacement. Okay, so we saw, for example, Dima talked about a new hybrid model from Google. He talked about multiple models, but I wanted to highlight here Neural GCM, this model that has a die-core embedded. So it's an actual numerical die-core built on first principles physics that is coupled to machine learning, essentially parameterizations and correctors that help it to be a really skillful NWP model. As he showed, comparative performance to the ECMWF model. We also saw in David Hall's talk another machine learning forecast model, the spherical Fourier network neural operator model that's on your right side there. And then this very, very new thing, like the paper just came out, I think it was last week or the week before last, on Climate in a Bottle, this new almost foundation model that can build essentially arbitrary but very realistic atmospheric states from either just from scratch, from hand points of samples of observations. So a lot of really new things that can be done with these models. And I just want to pause before going on to say that all these developments, there's a lot of low-hanging fruit here because the developments that we're seeing are people creating these models and evaluating them, showing that they're working amazingly, but they don't have the person power to actually be evaluating them in depth. And that was part of why we wanted to do this machine learning component to DCMIP, is to try and get more people familiarized with these models to actually start to evaluate them more. And I say this from personal experience. In the Cascade project, Calibrated and Systematic Characterization, Attribution, and Detection of Extremes, it's the Department of Energy project that I've been involved with for over 10 years. We've been collaborating with NVIDIA directly. They're developing all these models. They've developed now, I think, three classes of SFNO type model over the several years that we've been working with them. They've been very, very eager to collaborate with us on evaluating their model because their efforts are really focused on developing the model and then developing the next best model. And that's the other thing to keep in mind. The developments are so fast right now. Even collaborating directly with NVIDIA, it's hard for us to keep up with their developments. It's so fast. And so the reason that I've increasingly become sort of embedded in the machine learning field was it was the emergence of these machine learning weather forecast emulators that really was the, oh, machine learning it's changing our field, because what it's doing is it's allowing us to ask scientific questions that we couldn't have before. And I just want to highlight two potential examples here. There's lots of examples that we could go into, and I'll show a few other potential uses. Very large ensembles, because as we've seen, these models are very computationally cheap, somewhere between 10,000 and 100 times 1,000 faster than traditional dynamical models, meaning you can afford absurdly large ensemble sizes, meaning you can probe statistical, into the tails of distributions in ways that you couldn't before. And if, and this is a very big if these models are a physically reasonable representation of the Earth system, we can actually ask questions about what causes these super, super extreme events. And that's a very big if that we're actively looking into. The other thing is the differentiability of property of these models is, I think, going to really open up a lot of new science. So on the huge ensemble size, and this is a slide provided by Ankur Mahesh, he has two papers on huge ensembles of neural network, I just forgot the acronym, Ankur. Huge ensembles of neural network simulation, sorry, HENS. So this approach of using traditional NWTP type approaches to generating ensembles plus multiple versions of the SFNO to generate ensembles that are order of magnitude like 10,000. First paper establishing that this can be done. Second paper establishing that you get really good reasonable statistics, and actually some cases outperforming IFS in terms of misses of extreme events. This particular event in Ankur's paper that I want to highlight here is a heat extreme in Kansas City, a moist heat wave, very, very hot, so heat index of about 43. The actual observation, did anyone else have luck with this pointer? Is it down? It's just buzzing out.
It just takes a while.
Oh, it just takes a while. Okay, I just need to be more patient. Thanks. So the star up there at the top is the observation. So we've got temperature on the x-axis, dew point on the y-axis. So the more to the upper diagonal you go, the higher the heat index. And this was really a very extreme heat wave. The IFS ensemble, roughly 30 or so ensemble members, all these red ones, none of them approached events that were either that hot or that humid. Whereas the HENS ensemble, you can see each individual dot is a prediction from one of the, I think it's close to 10,000 ensemble members. Quite a few of them actually made it up into that range. Quite a few of them actually show this second lobe of potential where you could have been in a slightly cooler, drier condition. IFS also had that. But the fact that we have this on huge ensemble size means that you can actually look at the risk of like really, really catastrophic type extremes that could really break infrastructure, cause lots of damages to human health. And as I alluded to in the Cascade project, we're looking into, can we use these types of models to understand what are the causes of these really, really extremes? The extremes that are so rare that we might only actually observe one in a century, if at all. Yeah. So the other aspect of machine learning models that I want to highlight here that I think there's maybe low-hanging fruit here, especially now that an increasing number of you are gaining competence with running these models on either your machine or on the NCAR machine. is the differentiability property. But first I want to say differentiability isn't new. Adjoint models have existed for a while. The ability to essentially do a linear sensitivity analysis on a dynamical core. The catch is this requires, so let's take a step back and think about all the dynamics that we learned about this week. All of the nitty-gritty mathematical details, the huge equation sets that need to be approximated by fairly sophisticated methods. Now imagine writing a linearized version of that and maintaining essentially two separate die-cores, one that's linear, one that's not. These adjoint models are relatively rare. They exist, but I'm going to go out on a limb, and actually I'd be curious if I'm wrong on this. For the dynamical cores that we're looking at in DCMIP, do any of them have adjoint models? Right, so, oh, yours does. Yeah, fair. So this is, adjoint models because they're relatively rare, it's hard for just the average grad student or just university PI to grab a model with an adjoint capability and actually use it. Machine learning models, by definition, by design, are backwards differentiable, which raises some really interesting things. So I just want to highlight an interesting way that one could use these. So let me start off with some definitions here. So I'm going to call M just the arbitrary operator that represents the machine learning forecast emulator. This might be the SFNO model that David Hall talked about, might be neural GCM. M to the N represents stepping this model forward N times in an autoregressive type of manner. X represents the state of the atmosphere, so all the state variables that we've talked about. And then one last thing I'm going to add here, let's imagine that we have an operator O that somehow you can detect cyclones or a cyclone in the output of the model. So you take the state X and you get the lat-long locations of that cyclone. But the catch is you design this operator in a way such that it's differentiable. And I can talk to you about this later. This is possible to do. I have written one up. So imagine then you step the model forward, n time steps. So you start with the initial condition xt, you run the model forward, you maybe get some tropical cyclones, and then you run this tropical cyclone detection operator on it. You get the lat and lon of that cyclone. Then you can backward differentiate, and this is very easy. I mean, these models are designed to apply the chain rule to the million to sometimes billions of parameters in these models, such that you can assess you can look at the derivative of either the latitude or the longitude to all of the points in the input state. So you can do things like sensitivity analysis. What observations most control the location or the location or the landfall location of a given cyclone. You might be able to use this, for example, a lot of ways that adjoint models are used are to inform real-time field campaigns, like where observation is going to be most valuable. But you can also do science with this. Like say that you wanted to be a mad scientist and do weather modification. What point in space might you need to modify energy a little bit to offshoot a hurricane in some direction? Kind of a crazy idea, but it's something that could easily and relatively cheaply be done with these machine learning models. So these are just a couple of examples that I gave. This comes from a paper by Paul Ulrich, which it's really kind of a shame that he's not here. He's gotten a lot of airtime. His name has been mentioned a lot in this meeting here. Both Josh Elms and I were co-authors on this paper with quite a few other authors. We came together, this came from a workshop last year where we were talking about how machine learning might be used and ways that we can really help move the field forward. And so S2S, or so seasonal to subseasonal prediction, decale prediction, this is, I think you saw David Hall talk about this a little bit, and also I think Dima Kokov as well. This is, I think in the next couple of years, we're going to start seeing S2S models. This HENS approach that I just talked about, so really large ensemble sizes to look at low likelihood but high impact events. Detection attribution. It's not so out of the question that one could train a machine learning model on a version of CAM that has greenhouse gases versus one that's not. And you could do storyline type detection attribution with a machine learning model and with large statistics to get robust statistics. There's increasing evidence, and I think we're going to see some really cool papers come out in the next year or so, that you might be able to even use machine learning models to look at climate sensitivity, which might sound crazy because that you might think that you might need to run a model way out of sample to look at that. And I think, like I said, you'll see some cool papers coming out in the next year showing that machine learning models can be used for this. To the extent that we can trust models, hypothesis testing, proper process understanding, I think there's a lot of work to be done before we can do this. Eventually, climate projections, climate impacts, and so on. Okay. But what are some of the barriers to moving forward in the near term? Well, one of them is compute capabilities. So training these models is very expensive. Training an SFNO-like model takes hundreds to thousands of compute nodes with many, many GPUs, large amounts of compute time. They are expensive to train. So basically you require supercomputing resources to train these, at least at the level of fidelity that has been shown in this workshop. I'm personally, and this relates to the next point, is that the learning curve for training and developing these models is pretty high right now because there's not curricular materials for training weather forecast emulators in the earth sciences. There's a lot of materials for deep learning, but there's not so much in our field. And this is a thing that I'm personally very interested in developing. I'm hoping in the next year to actually have some online open curriculum materials for training fairly small models, like training on the NCEP low resolution data set, but emulating that. That's actually something that is actually doable on a desktop machine. But the last and biggest barrier to moving forward is trust in these models. And I know just from personal experience, I don't trust these models in a lot of ways, increasingly becoming intrigued by how good the physical fidelity is, but I think there's a lot of work to be done. And I know from talking to a lot of people that a lot of people are really resistant to doing science with machine learning models. So I want to pose a question, actually. Why do we trust dynamical models? And this is I want this to be interactive. I'm very, very curious what your opinions are. I have some ideas here too.
We've gone through centuries, well not centuries, but there's just a lot more validation, like a lot more tests.
Yeah, so a couple things I heard there. So decades of development, a lot of testing and scrutiny has gone into them over the several decades of development. Yeah.
I was just going to say, there's a lot of physics that we capture in there, basic physics principles.
So we start from first principles, yeah.
Repeat, I mean, they're based on one of the laws of thermodynamics.
Yeah.
I agree with what everyone's going to say, but I might be about.
Please.
I feel like working in a dynamical core. There's lots of key and embarrassing things that the public doesn't know about, that our users, the people who run the climate models, don't know about. So I've seen people make this case and say, well, is the machine learning model any worse?
Yeah, and I want to say, I'm not trying to say we shouldn't trust dynamical models, but I also have that opinion that they are approximations of the first principles, and I think that is important to recognize.
The mathematics has been designed to preserve and complement the physics, whereas a lot of machine learning, the math is designed for image processing.
Very true. There's one other one I'm looking for. I'm curious if anyone, yeah.
They kind of work.
By demonstration, yeah, okay, that's fair. Yeah, they do work. And actually, well, let me, Kwesi, and then I'll make my point.
I think because we have control over the dynamical models more than we have over the machine learning models. Sometimes machine learning models can be black boxes, and you just put in data, it trains on something, and gives you an output that looks like what you trained on. So,
fair point. I will say this does relate to the, it relates to another discussion point. I mean, I think to the majority of people, climate models are black boxes too. I would say there's probably order of magnitude, and I'm just guesstimating here, order of magnitude, maybe 100 people on Earth who really understand climate models. There's probably order of magnitude 1,000 to 10,000 people who either use them directly or use their outputs. So, the thing that I didn't hear here, which relates to this workshop, is, and this goes actually back to a paper by Schneider in 1979, this idea of developing hierarchies of model evaluation so that we develop them from very, very simple models and become incrementally more complex. And we find bugs in them. And this is one of the other ways that dynamical models are approximations. I guarantee you there are bugs in CESM, in an E3SM. There are millions of lines of code. There's no way there's not. And that's okay. So they're not perfect, but we build trust in them by going through these hierarchies and these idealized types of tests. So this hierarchical testing was really, this was the main point actually of the Ulrich et al. Paper that I alluded to earlier. This is the big point that we wanted to make, is that we need to start developing a hierarchy of tests for machine learning models that parallels what has been done in the climate modeling community. That's sort of a prerequisite to developing trust within the community. The other thing is this testing probably needs to be independent. It can't be the model developers themselves running these tests. It has to be something akin to the program for climate model diagnostics and intercomparison who runs these, so that there's not this feeling that NVIDIA is just showing us their best results and they're cherry picking them. And so this is the reason that I was very interested and very happy when Christian invited me to DCMIP. This is exactly what I've been wanting to do, is start to develop the types of tests that we're looking at. It was really great to have a lot of interaction yesterday in our Plan B scenario, a lot of really great ideas on new tests that we might be able to do, hoping we'll be able to maybe collaborate and write papers together on these new tests. The other point that I want to make, and this actually, we saw a lot of this in Cecile's talk, relates to this concept called component level understanding. We trust these models because they're developed in component ways. We understand what those components do, how they interact. A lot of the problems that Cecile talked about that were like the Labrador Sea problem, or earlier than that, the North Pacific cold bias, those were diagnosed by the model developers having a very good understanding of how this model works, what the likely culprits were, ways of being able to turn things on and off in these models in order to figure out what the problem ultimately was. Right now, that's not something we can do very well in machine learning models. Right now, they're structured in such a way that you cannot easily turn things on and off. And I think this is one of the very near-term next steps in machine learning model development, is structuring them in ways that mimic climate models a bit more, so that we can gain this component level understanding. And this, some colleagues and I, and actually Rich Neal as well, ended up joining us on this paper, have a paper on this in GMD that came out a little earlier this year. The first two authors, this is just a side note, they're philosophers of science, actually. This is a really, if you ever get a chance to collaborate with philosophers of science, particularly philosophers of science who identify as philosophers in science, so philosophers who actually have a lot of training in the scientific fields that they do work on, really productive, just enlightening conversations. And so we collaborated on this paper where we argue that in order to gain trust in machine learning models, we need to move beyond where the field is right now. I would argue that a lot of the papers that you see where people are developing understanding of machine learning models in earth science, they're using explainable AI methods. XAI, we heard a little bit about that in Will's talk. This is like you take the derivative of an output with respect to an input and see what aspects of the input are causing the machine learning model to, for example, predict an atmospheric river. These are really this is what we call a statistical understanding. It treats the model as a black box. You don't need any understanding of how the model works for that. I'm not saying it's not valuable, but in order for us to gain trust and also develop these models better, we need to both have people who have this component level understanding of machine learning models and develop them in such a way that they're amenable to that. I'll just say as an aside that one of the, I don't think I need to elaborate on this, since I think Cecile's talk gave a lot of really good examples of component level understanding in the dynamical model world. But I will say here that we can see the progress across climate models altogether here in this figure that shows cloud radiative forcing across 3 IPCC cycles. While the spread has increased, we're more confident that it's positive, and this is largely because of one of the things, really major changes that people identified as being a big uncertainty in cloud radiative forcing early on was our treatment of boundary layer turbulence and boundary layer clouds. And that has become increasingly sophisticated in models up to the most recent AR6. And that's directly attributable to people's component level understanding of how low clouds are produced in models, and that it's these cloud top radiative cooling drives turbulence in these boundary layers and how we represent that. So what's going to happen in the next 3 years? And this is where I'm really guessing. So I think in the next, probably within a year, we're going to start seeing seasonal to sub-seasonal model papers that are showing skill that maybe even starts to go beyond S2S modeling capabilities with dynamical models. This is just a guess. There's a big question here of to what degree are the things that we want to look at in S2S actually predictable? There's questions about the limits of predictability, but machine learning models by demonstration could show that we have a lot more predictability than our current modeling capabilities provide right now. I'm hoping to be one of the people who would love to collaborate with folks on this, more weather and climate focused curricula for machine learning, so that students and postdocs and early career folks can get up to speed really quickly without having to go to a lot of disparate resources to figure out how these models work, how to train them, how to use them. I will say I do have some slides at the end of this deck. In this deck you can get on the DCMIP website with links that I've found useful over time for building my understanding. What I'm hoping also is that we'll see an increase in smaller models. And when I say smaller models, models that have fewer parameters but they're still competitive. And the reason I'm hopeful and think that we'll start to see more of these is that the current class of models like neural GCM and SFNO, they're even difficult to run on a laptop. So I'll say from personal experience, yesterday, I attempted to run SFNO on my laptop. I don't have enough memory, even with running on CPU, to run it on my laptop. It's too large of a model. So these smaller models are barriers to the masses, and not just NVIDIA, developing and understanding these models. I also think it's imminent. We're going to see fully machine learning based reanalyses, reconstructions of the past that are based on machine learning models fused with observations and not actually being trained on Error 5 at all. Next 3 to 5 years, we might have some really big jumps in subseasonal to seasonal prediction capabilities. I'm hopeful of that, but we'll see what happens. I think these hybrid machine learning models are going to become increasingly prevalent, like neural GCM or models like CAM having parameterizations built in them as components that can be used. We'll see foundation models, and actually these last 2 points are kind of linked. So nobody's done this yet, but one of the interesting things that could be done, a lot of the current class of models, they embed knowledge in high-dimensional vector spaces, and this is what large language models do, and this is how diffusion-type models work. They encode information in some way in these high-dimensional spaces, and they encode both language concepts and image concepts using the same types of vectors, and this is how we can get sort of interactions between text and images. Like with diffusion-type models, you type a prompt, you get an image, or you can have a large language model describe what it sees in an image. I think it's very plausible that we're going to see large language models fused with Earth system models. One of the data sets that I don't think anyone has taken advantage of are the forecast discussions in the US National Weather Service. There's an enormous database of text describing people, what meteorologists see in multiple times a day in meteorological fields that could very easily fused with these large language models and develop really new types of models where you can interact with the output of what these models are producing in very novel ways that I can't even guess at right now. 5 years plus, I guarantee you dynamical models will still be around. They're going to absolutely be essential. There's no way that we're going to replace them, partly because we're never going to fully trust machine learning models to give us the answers to our biggest, most important questions. Where a lot of the experiments, knowledge that's generated with machine learning models, I'm certain will almost always be duplicated or verified in some way with a dynamical model. I think also it might be less than 5 years. I'm not sure where to put this. I think we're going to see CMIP type contributions at kilometer scale resolutions with these large models, with machine learning type forecast models. What do we do with them? I don't know. They're going to be hard to work with. That's a lot of data. Will we see climate sensitivity reduced? I don't know. It's a tough problem, but yeah. So with that, like I said, there's some resources, and thanks all.
So you talked about the advantages of having differentiable die core. The neural GCM dynamical core is hydrostatic and coarse resolution because they needed to do it in a year and because it needs to fit in the memory of one TPU. Do you see advantages to taking a model like CAM-SE that's non-hydrostatic, capable of high resolution, and putting in the probably several years worth of work to make it differentiable?
I'm going to go with my gut answer. No, I think not. And the reason I think not relates to a point that Dima made is that if you're going to, the parameterizations are going to correct a lot of the sins of the die core. I mean, I'm sure there can be advances by developing the die cores better and maybe more sophisticated so that you can offload. I think I'm actually almost mimicking Dima's response here, but I very much agree with his take on that. I guess the question is, how much of the physics do you want to offload to the machine learning components? And that's an open question. I mean, maybe some of that physics you could get by just going to higher resolution with your sort of easy to produce die-core. I don't know.
So how do you balance the hope for hierarchical approaches with the speed at which industry likes to go straight to state of the art? That was a big struggle of my work.
Yeah, it's been a struggle for us too. Every time we try and do something new, they've come out with a different way of running these models that kind of breaks what we're originally trying to do. I don't know. That's an ongoing problem. I think the increased interaction and dialogue with the people who are making these models, the more that we can sell them on the value of these types of tests for both building trust in these models and getting more and more people to use them, I think the more that they're going to be agreeable to using at least stable software interfaces to running models. I'm hopeful that Earth 2 Studio actually might be stable at least for a year. Yeah, but I don't know. That is a big challenge.
Crazy.
Thanks a lot, Travis, for this talk. So I have this question about the ML MIPS. Do you think there's going to be a time where we have a benchmark, just like the CMIP experiments, where you have like a specific target that you want to attain, like with this ML models, and how do we get there?
Short answer, yes. How do we get there? I think developing the hierarchical approaches first is the way that we get there. I think if we start trying to do CMIP type intercomparisons with these models, it's going to be a waste of time because no one's going to believe them. Yeah.
Yeah, Gus?
Can you comment on the models that use generative AI? I mean, whenever we use generative AI, we need to prompt them somehow. Could that be introducing bias into these models, do you think?
I don't know how to answer that. That's a very interesting question. I would have to think about that a bit. I mean, I guess the first thing that comes to mind, if we go back to the example of climate in a bottle, one of the capabilities that this has is that you don't have to initialize from random noise, but say for example that you have partial satellite image, it'll try and fill in the rest. So in that sense, you're intentionally biasing what it's doing. Whether that bias is in the region where you're inferring information in some negative way, I don't know. I have no idea how to. I think that's an interesting science question, probably. Yeah.
We have one more, and then I have a couple of announcements, so don't run off. Yeah.
So thanks for the great talk. I was interested in the point of getting smaller models for AI driven, and I'm kind of confused by how a smaller models can be, because when we ask for a dynamical smaller models, we just reduce the number of terms in the momentum equation, and when we want to improve it, we just sum more terms. What is for machine learning model? Do we is the same size of the data set? Do we need to change architecture? Can we be guaranteed that the smaller models can be comparable to the larger one?
It's a really good question. So I'll give an example. So if you were to take an out-of-the-box, just a deep convolutional neural network, you could get that architecture off of Hugging Face or something like that, and train it. It's not going to be as train it to be an autoregressive type model. And people did this. This was some of the earliest work in machine learning forecast emulators. I use this type of approach. It's not going to be as skillful as a model that's architecture is intentionally designed to be skillful for this problem. So like NVIDIA's work, their affine Fourier neural network operator architecture was designed to have these Fourier operators that mimic the differential operators that we see in dynamical models. And the idea is you learn what those operators are. So they, in some way, they've biased the architecture of the model to get the right answer. The problem with AFNO was they used Fourier transforms, and that was a problem very quickly. As you can imagine, we're on a sphere. It's not the Fourier sine cosine waves aren't the basis function on the sphere, so they had major ringing problems that caused the model to not be as skillful. Their next model then went to spherical harmonic operators. So each of these evolutions caused that allow these architectures to be more skillful with comparable levels of parameters. So I think that part of it's going to be architectures that are more intentionally designed. But there's the last part of your question is open. Can you, even with architectural advances, can you make smaller models that are as skillful, or at least skillful enough to be useful for some science cases? I don't know. That's to be determined. Yeah.
So let's thank Travis again. Okay, 3 announcements. Number 1, the weather isn't cooperating, so we will have an indoor dinner. Unfortunately, we were hoping to have an outdoor dinner on the Tree Plaza. We shift that into the NCAR cafeteria where we have the lunch. Well, of course, if the weather is dry, we might just head out after we have eaten and spend another, I don't know, an hour or so, on the Tree Plaza, but without the setup, and just, enjoy the evening there if it's not too cold or not too rainy. Yeah, that's number 1. Okay, number 2, we will be heading back here at 3:30 for final presentations. We have a 2-hour time block. And I really would like you not to stress out about it. Yeah, we asked basically the modeling groups, and as we know, we have these 4 teams, and we basically have like half an hour per theme, like MPAS, FE3, SE, and machine learning, to put things onto the webpage. Yeah, we want to use the webpage as our communication tool. You can figure it out as you want, how you want to do it. If you want to come here as a group, we have M+1, M+2. If you want to come here as a group, that's fine. Everybody could, spend 2 minutes. It's only boiling down maybe 2 minutes per person. Yeah, so don't stress out. Pick something you find interesting, a highlight. Or you can decide if you have one speaker, if you decide on one person representing on behalf of the group, and that person would then do it here on behalf of that group. That would also be fine. I'll let you figure that out. I would like to remind you there's not a lot of time to get ready. Yeah? So we will have lunch here in a minute. We then head back to the library. There will be snacks a little earlier today at 3 instead of 3:30. Yeah, so 3:15. So it's the snack break 3 to 3:30, and then 3:30 you want to come back here. So you want to be very considerate. We only have like an hour and a half to do this. Doesn't need to be perfect. A screenshot of NCView, NCVis is fine if you put a little augmentation around it. Not perfect. Or if you get the Jupyter notebooks or Jupyter to run Casper, as I think is up, up and running. Again, and you can talk about all test cases, maybe a few, whatever is interesting. And last but not least, I want to actually introduce you to a former colleague of mine who is a guest, sorry to put you on the spot, Ricky, who actually visits us here at DCMIP today, who was working at NASA with S.J. Lin back in the days when they developed the S.J. Lin finite, it's the Lin-Root, back then it was called the Lin-Root finite volume dynamical core. We heard a lot about that. That's the basis for FE3. And back when Ricky was at NASA, S.J. Lin was at NASA, and they co-developed the advection scheme and also the shallow water model. A little later, S.J. Lin took it forward to build the 3D model, but he was a colleague of mine at the University of Michigan until recently, and I want to just, Ricky, maybe if you might say a word, if you like.
I don't trust dynamical cores. And Mike Navone wrote a tangent linear model for Lin and Root in 1998, which I think is still operational as it's evolved to do sensitivity analyses and forecasts at NASA.
Right. So I don't know, Ricky, whether you have time to stay for lunch.
I came to sort of have lunch.
All right, so if any of you are interested in talking to Ricky over lunch, grab him. And let's come back here at 3:30, but have lunch, speed in library, and we're back here at